Hi everyone, this is the tutorial on deep reinforcement learning, decision making, and control. So if that's not the tutorial that you were looking for, you should probably find the correct room. We have all of the slides for this presentation online at the URL up there. So if you're interested in following along the slides as we go along, go to that URL and check out the PDF on that site. Okay. So first, for some introductions, my name is Chelsea Finn. I'm a PhD student at UC Berkeley.
And I'm Sergey Levin. I'm an assistant professor at UC Berkeley.
And a lot of our research focuses on autonomously learning complex sensory motor skills from scratch. And so some of the videos here show some of the work done in our research. We focus a lot on robotic learning as a test bed for our methods, but the methods that we'll be talking about today and the methods that we develop are only applicable to robotics and are applicable to a number of domains as well. Okay, so the topic of this tutorial is going to be on deep learning for sequential decision making. And what we mean by sequential decision making is the ability to take actions that affect outcomes and try to reason about those outcomes to take the actions, to figure out what actions that we want to take. So first, when do you not need sequential decision making? You don't need sequential decision making when your system is going to make a single isolated decision, for example, classification or regression. And in particular, when the decision that it makes doesn't affect the future decisions that it will make in the future. Namely, when it won't affect the state of the world and the decisions that it wants to make in the future. So some common applications of sequential decision making I'll show up here. These aren't the only applications that of this problem, and I hope that some of you came today with your own applications in mind. So as I showed before, robotics is a very common application of sequential decision making, as is autonomous driving, language and dialogue, and more broadly the problem of structured prediction, where you're trying to make predictions of sequentially. Business operations, or such as resource management and allocation, and finance, where you're trying to make predictions about financial markets. And beyond these applications, the ability to make decisions in sequence is a key aspect of human intelligence and something that humans are able to do very effectively. Okay, so why do we want to use deep reinforcement learning in the first place to solve these sorts of problems? Well, we want our agents to be able to interpret rich sensory inputs such as vision, sight, touch, smell, and deep learning is really good at this. We want our agents to be able to handle raw sensory inputs that it's observing, and deep learning is a powerful mechanism for being able to handle such inputs. And beyond inputs, we also want our agents to be able to continuously take actions that affect outcomes, and then see those outcomes and take actions again to achieve the outcome that the system wants to make. And reinforcement learning is really good at that because reinforcement learning can reason about the outcomes that are going to occur once you take actions. And so in this tutorial, we're going to be talking about deep reinforcement learning and the ability to use deep networks to represent the mapping from sensors to actions. And this subsumes the problem of estimation, the problem of control, etc. And it's not just about taking a deep neural network and applying it to a reinforcement learning algorithm that can handle linear function approximators, for example. In this tutorial, we're going to be focusing on algorithms that can scale to very large high-dimensional functions so that we can effectively perform reinforcement learning with rich sensory inputs while taking continuous actions. Okay, so here's a tutorial. Here's an outline of the tutorial that we're going to be giving. First, Sergey is going to cover the reinforcement learning problem setup, as well as fundamental topics in model-free reinforcement learning, such as policy gradients, actor-critic algorithms, and value functions. Then we'll take a short break. After the break, we're going to be covering more advanced topics like soft optimality, inverse reinforcement learning, model-based reinforcement learning, and frontiers and open challenges in this setting. I'll hand it over to Sergey now.
All right. So let me start off by setting up the reinforcement learning problem, and then I'll talk about some kind of fundamental algorithms for model-free RL. So I'll begin with something that I think most of you are probably familiar with, which is a very classic kind of supervised learning problem. So if you imagine, for example, the problem of image recognition. In image recognition, you observe an image, and I'm going to call that observation O, because the word observation starts with O. You're going to do something to that image, and then you're going to make a prediction about the label of that image. And I'll call the label A to denote action. So we'll say that the action is the label that you're going to output. So I'll use this funny terminology because it'll be the same as the terminology we'll use later for reinforcement learning. And then if you want to classify images, a very good way to do it today is to use a large convolutional neural network. And this convolutional neural network outputs a probability distribution over the class of that image. So I'm going to call that distribution A given O, and I'm going to denote the learned distribution with pi. And pi stands for policy. So you can view supervised learning as learning a very simple policy that looks at an image and outputs a distribution over labels. And this policy is parameterized with parameters theta. In the case of a convolutional neural network, theta simply denotes all of the weights in the convolutional neural network. So you can view this supervised learning problem as a very simple kind of decision-making problem. Okay, so let's gradually transform the supervised learning problem into a sequential decision-making problem. When you look at this picture and you try to recognize, for example, whether or not it contains a tiger, your ability to output the correct label for the picture is going to strongly determine what you observe next. So if you're incorrect in detecting the tiger, you might see something very undesirable at the next time step. So to turn this into a sequential decision-making process, we'll first put a subscript of t on everything to communicate the fact that these are part of a sequential process. And I'll draw this arrow here to show that the action that you take is going to affect the next observation. So the key thing that's going to distinguish sequential decision-making from a standard kind of IID supervised learning setting is that the action you take determines the next observation. Okay, so now we have something that looks like a sequential decision-making problem. We can change our action space a little bit so that it makes a little more sense. We can say, well, maybe instead of outputting a label, you're going to output a distribution of potential actions you might take. And some of these actions might have good outcomes, some of them might have bad outcomes. So there's a number of different actions you can take that'll determine the next observation. The actions can be discrete, in which case your policy might be represented with a network that has a softmax at the end. They might also be continuous, in which case your neural network might output the parameters of some kind of continuous distribution, like a Gaussian. Okay, so now a little bit of terminology. So O here denotes observation. That's the thing that your policy gets to see to make a decision. A denotes the action, so your policy outputs a distribution over these. Your policy, in general, is a distribution over action, condition, observations, although it's very important for us to also introduce a notion of state. And I'll explain the distinction between state and observation in a second. Sometimes we'll actually use A given S to denote the policy if we don't want to deal with problems of partial observability. So here's the distinction between state and observation. If you see a picture of a cheetah chasing a gazelle, the picture consists of pixels. You get all those pixels as input, and that's your observation. So it's actually just the image pixels. But underlying this image, there's some kind of dynamical system that involves the state of these two animals, their velocities, and so on. And that's the state of the system. So here's a very important thing that distinguishes observations from states. If there's something else in this picture that blocks your view of the cheetah is still there. So you might not be able to fully infer the state from the observation because of things like this, because of partial observability, because of occlusions, and so on. The state is the kind of minimal sufficient description of the underlying dynamical system, and the observation is what you get to see of that, which might not contain all the information to infer the underlying state. Now, we can make this a bit more formal. We can actually draw a graphical model that relates states, observations, and actions. In the partially observed case, the policy is a distribution over actions given states. The state and action determines the next state. So this is sometimes referred to as the transition dynamics or the transition function or the transition distribution. And crucially in this graphical model, you can see that if you know the state, let's say S2, then all future states, S3, S4, and so on, are conditionally independent of all previous states, S1, etc. So this is the important thing that distinguishes states from observations. States cause future states to be conditionally independent of past states. And this is referred to as the Markov property. So if you know the current state, that is all you need to know to make the current decision. But knowing the observation might not be enough because the observations by themselves are not conditionally independent of one another, only given the states. Okay, so now that we've introduced states, observations, and actions, one very simple way that we can begin thinking about learning policies is to do the same thing that we were already very familiar with doing, namely supervised learning. So we might, for example, well, let's first switch to a problem that's maybe of a little bit greater practical value. Let's say that we'd like to look at images from a camera on a car and choose actions to drive that car. One way that we can begin to approach this problem is to collect a large data set of people driving cars. That data set consists of videos that are sequences of observations, sequences of images, and for each image, there's a corresponding action that the human driver took. This goes into a big data set, and then we can do supervised learning to train Pi on that data set and get a policy. That's a very reasonable way to learn policies if you have access to large amounts of data from a human expert, and this is sometimes referred to as imitation learning. We won't talk about imitation learning too much in this tutorial, but it is a very important topic when it comes to sequential decision making. However, if you'd like to learn complex policies without the requirement of having human data, you might want to do this, for example, if you'd like to do better than a human demonstrator, or if you're trying to solve a task where people aren't very good at demonstrating good behavior, you need some other way to define what it is that you want your policy to do. And the way that you define what you want your policy to do in reinforcement learning is by specifying what's called a reward function. So the reward function tells you which actions and states are better or worse. The reward function is a function of the state and the action. Sometimes we might use rewards that are only a function of the state. Occasionally we might use one that's only a function of the action, but in general they're a function of both. And they tell you which conditions are more or less desirable. For example, if you'd like to drive the car, a situation where the car is happily driving down the road, ideally on the correct side. If you're in Australia, this is not what the Americans expect, but still, whatever the correct side is, not getting into any accidents, going at the desired speed, that's probably a state where you have high reward. If your car is in an accident, that's something that you might say has low reward. Now, the crucial thing about the reward function is that your goal is not to pick the actions that will get you the best reward function right away, but to take the actions that will give you the best reward function summed over your entire existence. So, for example, if you're driving the car, you might choose to not enter a particularly dangerous intersection, for instance, not because you're afraid that you'll immediately come into an accident, but because you're afraid that the long-term consequence of that action will decrease your expected rewards. So we care about long-term sums of rewards, not your immediate reward. So now we've defined everything that we need to specify a reinforcement learning problem. We have the state S, we have the action A, we have the reward function, which is a function of the state and action, and we have the transition dynamics, which govern how the states evolve. And together these define a Markov decision process. If you have observations and your policy depends on the observations, not on the states, then you have what's called a partially observed Markov decision process. When I talk about model-free algorithms in the first half of this tutorial, I'll mainly focus on fully observed Markov decision processes, so I won't talk about observations very much, and we'll see policies that depend only on the state. But we'll come back to the notion of observations later in the second half when Chelsea talks about model-based reinforcement learning. Okay, so for now, we'll just talk about states and we'll forget about observations until the second half. So now we can formally write down the objective for reinforcement learning. We're going to have our policy, pi theta, where, again, we'll come back to the partially observed later. Theta corresponds to the weights in a deep neural network or whatever representation you have for your policy. The policy takes in the states, outputs the actions. Both the state and action go to the environment. The environment has some generally unknown transition dynamics that are going to determine what the next state is, and the next state is then fed into the policy. The policy and the transition dynamics together induce what's called the trajectory distribution. So the trajectory distribution is a probability distribution over sequences of states and actions. For shorthand, I'll denote this as pi theta tau, where tau is a sequence of states and actions, and I'll say this is a trajectory distribution induced by pi. But here I've written down what this distribution actually is. It's the product of the initial state distribution times the probability of taking an action times the probability of getting the next state given that state in action, and then you keep multiplying these until the end of time. And I'm going to use capital T to denote the length of a trajectory. One very useful object that we can derive from the trajectory distribution is what's called the state action marginal. So this is the probability of being in a certain state and taking a certain action at some time step. And we can obtain this by taking the entire trajectory distribution and marginalizing out all the other states and actions. If you have an infinitely long trajectory, you can still reason about state action marginals, but then to do that, what we have to note is that this, the product of these two probabilities here actually defines a Markov chain on S. So if you have a Markov chain and you have an infinitely long trajectory, that Markov chain, under a few regularizing assumptions, will settle into a stationary distribution. So if you have an infinitely long trajectory, you can't compute a state action marginal at every time step because there's infinitely many of them, but you can still reason about its stationary distribution. So this will allow us to also analyze the case of infinitely long trajectories. So in the infinite horizon case, the goal of reinforcement learning is to maximize the expectation of the reward under the stationary distribution with respect to the policy parameters. And in the finite horizon case, the goal is to maximize the sum of expected rewards under the state action marginals. So this is the finite horizon case. So in both cases, what you're doing is you're maximizing the expected total reward of your policy. That's the objective that we're trying to solve when we do reinforcement learning, and there are many different ways to go about trying to attack this problem. A quick aside before I introduce some reinforcement learning algorithms about notation. So in this tutorial, we're going to use S to denote state, A to denote action, and R of S comma A to denote reward function. This notation was popularized actually by Richard Bellman for dynamic programming, and it's widely in use today in reinforcement learning. If you read some papers, especially in robotics, on this topic, you might encounter a different notation where X is used to denote state, U is used to denote action, and instead of rewards, we have costs. This notation was primarily popularized in optimal control by people like Lev Panteryagin, where X denotes a state because that's a very common letter to denote an unknown variable. U denotes action because U is the first letter for action in Russian. And we have costs instead of rewards, I guess because optimal control people are a bit more pessimistic. So there's no formal distinction between these two notations. Reward is just the negative of the cost. So they're exactly the same. So if you see X's, U's, and C's, keep in mind that it's exactly the same thing, and all the stuff I'm going to say for S's, A's, and R's still applies. All right. So let's get started with our first reinforcement learning algorithm. I'll introduce a very general kind of anatomy of reinforcement learning algorithms that I'll come back to throughout the tutorial. For pretty much any reinforcement learning algorithm that we're going to describe, it consists of three parts. The first part is to generate samples. So what that means is take your current policy and run it. If you're learning on a robot, you run it on your robot. If you're learning in a simulator, you run it in your simulator. Whatever system you're trying to control, execute your policy on that system and collect samples. These are also sometimes referred to as rollouts. Then what you want to do is you want to take those samples and analyze them in some way to fit some sort of model or estimator of how well you're doing. This model or estimator might be very simple or it might be very complex depending on which algorithm you're using. And then once you have that estimator, you can use it to improve your policy. So pretty much any reinforcement learning algorithm will have these three steps: generating samples, fitting some kind of model or estimator, and then using that model or estimator to improve your policy. Sometimes these steps can be very complex, or sometimes they can be very simple. So I'll cover, for example, policy gradient algorithms where the estimator just consists of summing together the rewards in your samples. Very simple, just a big summation. Algorithms like Q-learning where you actually fit a neural network in this step to your returns. And then Chelsea will talk about model-based algorithms where you actually fit a fairly complex dynamics model to your samples. Policy improvement, again, can be very simple with policy gradient. It's just a gradient ascent step. For Q-learning, it might just be maximizing your Q function with respect to the action. And for model-based learning, it might involve actually propagating gradients through your model and improving your policy with many steps of gradient descent. So these steps can range a lot in terms of their complexity. All right, so now let's talk about policy gradients. I'll introduce this as the first reinforcement learning algorithm because in some ways it's actually quite elegant and simple and reasonably easy to think about. So policy gradients is basically a method of directly differentiating your objective. So our objective in reinforcement learning, I'll use the finite horizon case in this section, simply consists of the sum over all the time steps of the expected reward of your policy under the state action marginals. And I'm going to use J of theta as shorthand for this objective. So it depends on theta. We're optimizing it with respect to theta. Now, recall that this is the equation for the trajectory distribution, and I'm going to use pi theta tau as shorthand here. So that means that I can rewrite J of theta a little more concisely as the expectation with respect to trajectories drawn from pi theta tau of r tau, where r tau is just shorthand for the sum of the rewards along all the steps in that trajectory. So this is just a more concise way of writing that same objective. And we can write it out also as an integral. The integral over all trajectories of the probability of that trajectory, pi theta tau, times this reward, r tau. This is just from the definition of expectations. If you have discrete states and actions, this would be a sum. And our goal with policy gradients is to compute the gradient of J of theta with respect to theta. So let's derive that gradient. We have the integral. We're going to put the gradient operator inside the integral. And now we're going to introduce a little identity that's going to be very, very crucial to deriving policy gradient algorithms. The identity is the following. If you have some probability, then pi tau times grad log pi tau is equal to pi tau times grad pi divided by pi tau. This is just from the definition of the derivative of a logarithm. And the top and bottom here cancels out, and you get just grad pi tau. This identity is very simple, but it's very crucial to deriving policy gradients. It says that pi tau grad log pi tau is equal to grad pi tau. And we're going to substitute this into our equation for the gradient, and we're going to get this. Now we have the integral of pi tau grad log pi tau r tau, and this is just an expectation under pi of tau. So we can write it as an expectation like this. So our return is the expectation under pi tau of r tau, and our gradient is the expectation under pi tau of grad log pi tau times r tau. So that's the equation for the gradient. Now, why is this useful? What have we actually done here? Well, it turns out that if we do this trick, we can compute the policy gradient without actually knowing the transition dynamics. Here's how we do that. Note up here the equation for the trajectory distribution. Let's plug it into log pi tau. So it's a product, so when we take the log, it's a sum of logs. The log of the initial state distribution plus the sum of the logs of all the actions plus the log of the transition dynamics. And we're taking the gradient of this with respect to theta. The first term, the initial state distribution, doesn't depend on theta, so its gradient is 0. And the last term, the transition dynamics, also doesn't depend on theta, so its gradient is also 0. So that means that this term, grad theta log pi theta tau, actually only depends on the probability of taking the actions along that trajectory and does not depend in any way on your transition dynamics or on your initial state distribution. So that means that we can write out the policy gradient like this. It's just the expectation with respect to trajectories sampled from your policy of the sum of the gradient log probabilities of all the actions along that trajectory times the sum of the rewards along that trajectory. And this we can compute without actually needing to know the transition dynamics, just by sampling. So here's how we can evaluate the policy gradient. Remember that this is the anatomy of our reinforcement learning algorithm. For the orange step for generating samples, that's what we're going to use to evaluate that expectation. For the green step of fitting of the return, we're just going to sum together the rewards along that trajectory. And for the blue step for improving the policy, we'll just increment our parameters by some step size times the policy gradient. So this will allow us to improve our policy. And we're going to use samples to approximate the gradient, so we can write it out as a sample-based estimator like this, where I just replace the expectation by a sum. And this allows us to write down the first reinforcement learning algorithm that we're going to talk about, which is called the reinforce algorithm. So step one is to generate samples by running your policy. So you do this by literally running your policy on your system, whatever it might be, whether it's a robot, a simulator, a car, whatever. You sum together the rewards along each of the trajectories and compute your gradient estimator. And then you just increment your parameters by some step size times the gradient. So this is just gradient descent for learning policies. And then you can repeat this process. Yes?
Can I ask a really stupid question?
Please.
If we have some sort of action which has a highly, highly negative reward, won't we just never do that, or like, want to do it less and less?
So if we have some action that has a highly negative reward, the question is, will we not do it, or will we do it less and less?
Won't the gradient just push us away from
Yes. So the answer is that, yes, the gradient will push you away from that action. And I'll actually come back to something related to this later on when I talk about baselines. So hold that question until then, and if it still comes up, let me know. Okay. So that's the reinforce algorithm, and we can build up kind of more sophisticated versions of this algorithm. They can actually be used to directly optimize neural network policies. So this video that you see here, this is actually a little humanoid simulated robot that learned to run using policy gradients, actually using an algorithm called TRPO, which I'll talk more about later. The only step here that's really a little bit non-trivial is to compute the gradient of the log probability of your policy. And in deep reinforcement learning, this is done with just standard backprop. So here's an example. If you have, let's say, a continuous action space, you might choose to represent your policy with a Gaussian, where the mean of that Gaussian is a neural network function of the state. So this is the equation for the log probability under that Gaussian. And if you take its gradient, then you get this. So you get sigma inverse FST minus AT times DFD theta. And those of you familiar with backprop will recognize that in order to compute this derivative, all you have to do is just backpropagate -1/2 sigma inverse FST minus AT through your neural network. So just standard backpropagation. And if you have discrete actions, same thing. You have a softmax at the top of your network. You can compute the gradient and backpropagate the error, just like you would in supervised learning. So everything here is straightforward and quite straightforward actually to implement with standard automatic differentiation packages. But let's actually try to understand a little bit better what it is that we just did here. So, okay, we have this equation. It seems a little bit opaque. It will push us away from bad actions, as the as was said before. But what is it actually doing? Like, what's the intuition behind the policy gradient? Okay, so let's write it down in a more concise way first. This will help us think about it a little bit. So we'll just say it's the gradient of the probability of a trajectory times the reward of that trajectory. And that means that it's going to do something like this. We're going to run our policy that will generate some trajectories. These are the black lines. We'll evaluate their reward. Some of them are good, some of them are not so good, and some of them are really bad. And when we take this gradient step, what it will do is it'll take the good trajectories and it will increase their probability. It'll take the bad trajectories and it will decrease their probability. And in this way, it'll get us a better policy. So the good stuff becomes more likely, the bad stuff becomes less likely, and that means that we're just kind of formalizing the notion of trial and error learning in a gradient descent algorithm. So a policy gradient is just a way to formalize trial and error learning. You make the good trajectories more likely under your policy and the bad trajectories less likely. Okay, so what's wrong with policy gradients? Why don't they solve all of our problems, and why do we need any other method? Well, there are a couple of pretty major challenges, and I'll talk about a few ways that those challenges have been addressed in the past. One challenge with policy gradients is that this estimator of the gradient has very high variance. There are a number of reasons for this, but one relatively simple reason to illustrate you can visualize is something like this. Let's say that you have this graph where the horizontal axis represents trajectory and the vertical axis represents the reward. So you can kind of crudely visualize your current policy with this curve. Maybe this is the probability that your current policy assigns to each trajectory. And then you generate some samples. Let's say you generated 3 samples. The leftmost one has a big negative reward, and the 2 on the right have kind of low positive reward. If you have these samples and you imagine what this gradient estimator will do, it'll probably push your policy a bit to the right so that it puts very little mass on that big negative sample and a little bit more mass on the small positive samples. But now, what if I take my reward and I add some constant to it? So if I add a constant to my reward, the solution shouldn't change because it's just a constant. So the best trajectory remains the best. So now these samples, they have the same relative rewards, but they're all just bigger. And now my gradient will actually be different. So it might actually choose to spread out this policy a little more widely instead of moving it to the right. In general, if I have an infinite number of samples, the gradient in expectation will be exactly the same. But for a finite, especially small number of samples, the gradient will be very different. So this is the problem of high variance with policy gradients. There are actually many other situations in which this problem manifests itself. There is another big problem with policy gradients. Let's imagine that I have the following policy. This is a very simple policy with just 2 parameters, k and sigma. So it's a one-dimensional state, one-dimensional action. The policy just consists of multiplying the state by a constant and then using that as the mean of a Gaussian. So sigma is the variance of that Gaussian. If I do policy gradient optimization with this policy parameterization and the reward that just says get the state to 0 and get the action to 0, so penalize squared state and penalize squared action, I can actually draw the vector field of the policy gradient, and it's going to look like this. This is from a paper by Peters and Schall. And what you can see from this vector field is that the gradients always try to decrease variance. That makes sense because the optimal policy has a variance of 0. They also try to move the controller gain towards the optimal value of -1, but the magnitude of the gradient for the gain is much smaller than the magnitude for the variance because you can very easily make your policy better just by reducing variance. And if you reduce the variance too much, then you won't have very much variability between your samples, and you won't be able to tell that you need to also change the gain. So the trouble is that even though the gradient points in the right direction, the terms are very different in size, and that causes the policy to prioritize reducing variance, which further reduces its ability to modify the gain. So the part of the cause behind this phenomena is that policy gradients take steps that are of a particular size in parameter space, but different parameters influence your probabilities by very different amounts. So this results in very slow convergence, and in practice makes it very hard to choose the right learning rate for policy gradients. So I'll talk about some ways that we can mitigate this problem as well. But first, let's talk about variance. I'll cover 2 methods for reducing variance in policy gradient. The first one is something simple that we can do by basically exploiting causality. So causality tells us that what the policy does at time step t prime doesn't affect the reward at time step t if t is less than t prime. That is, if you take an action, no matter what action you take, it's not going to change something that happened in the past. You can't change the past. And we can actually exploit this to write down a lower variance version of the policy gradient. So here, I haven't changed the gradient at all yet. All I've done is I've taken the sum around the log pi, and I've distributed the rewards inside that sum. So now you have a sum over t from 1 to t of log pi times the sum of t prime from 1 to t of the rewards. It's the same exact estimator. I've just distributed the sums inside. But now you can see here that the grad log pi times step t is multiplied by the sum of rewards over all the steps. But it can't affect the reward at steps less than t. So we can use this here by just changing that 1 to a t. So now we're going to multiply grad log pi times step t by the sum of all the rewards from now until the end, rather than from the beginning to the end. And this is sometimes referred to as the reward to go. And we can use q hat it as shorthand to denote this. So we can write down a lower variance of version of the policy gradient like this. Just the sum from t equals 1 to t of grad log pi times the reward to go. And this will get us lower variance. There's another thing we can do to reduce the variance of the policy gradient a bit. Remember this diagram where we generated some trajectories and then we made the good ones more likely and the bad ones less likely. This wasn't quite correct because if your rewards are all really, really big, well, then what your policy gradient is really trying to do is it's trying to make the probability of all the trajectories a little bit higher. It can't quite do that all the time, but that's what it's trying to do. So we'd like to do something to cause it to actually make the trajectories that are better than usual more likely and worse than usual less likely, rather than looking at the absolute value of the reward. So I think we kind of know what we want to do. We want to do something like this. We want to take the rewards and just subtract out the average reward. That just makes it take the rewards that are a little better than what you expected and make them more likely and worse than you expected and make them less likely. That kind of makes sense. That seems like a better version of trial and error. But are we actually allowed to do that? Like, is this mathematically okay? It turns out it actually is. It turns out that if we do this, in expectation, the gradient is still exactly the same. And we can prove this pretty easily. Let's just take this new term that we added. If we distribute the grad log pi's inside, we get expectation of grad log pi times b, where b is a constant. So b is a constant in the sense that it doesn't depend on theta. That's equal to the integral of pi tau times grad log pi tau times b. And if we use the identity that we used before for policy gradient, but in reverse, we can show that this is, of course, equal to grad pi tau times b. Now we can take the gradient out of the integral and we can take b out of the integral. So we get b times the gradient of the integral of a probability distribution. That of course integrates to 1. So we have b times the gradient of 1, which is 0. So that means that in expectation, subtracting this b term does not change the gradient. It does, however, change the variance of that estimator when you have a finite number of samples. And if you choose b carefully, it'll reduce that variance. So subtracting a baseline is unbiased in expectation. The average reward is actually not the best baseline, but it's actually pretty good and it's very easy to compute. So in practice, we often use average reward as the baseline, and it goes a long way towards making the policy gradient estimates better. Now, we can get a little more fancy. We can actually choose b to not be a constant, and in some cases this is still okay. This is sometimes referred to as control variance. For instance, we can take this estimator with the reward to go, and we can subtract some state-dependent baseline. The state-dependent baseline is still unbiased because the distribution here is with respect to A. It's A given S. So the same theorem as the one on the last slide still shows that this is unbiased. You can also try subtracting a baseline that depends on both the state and the action. If you fit the right baseline here, the values, the Q minus BSA, might get really small, which will further reduce your variance. The trouble is that this is no longer unbiased because the theorem on the previous slide does not apply. And if you want to do this, you have to add a correction term. You basically have to add the gradient of the expectation of that control variate. And in some cases, this might be very convenient to do. So if you choose the control variate carefully, this term might actually be something you can integrate analytically. For example, if you have a quadratic baseline and a Gaussian policy, the expectation of a quadratic under a Gaussian can be computed analytically. So if you want to learn more about this, there's a paper by Shixian Gu from 2016 that talks about this in more detail. All right. So the last topic I'll cover for policy gradients is the natural policy gradient. And this is that problem that I showed before where the gradient might not be scaled the same way in different directions, causing your policy to do some bad stuff like improve very slowly along some parameter value. So the trouble here is that when you take a gradient step, you're taking a step that's of a particular size with respect to the parameters. But different parameters change the probabilities of the policy to different degrees. So some parameter might change the probabilities a lot, another one might change it very little, because your policy, of course, is a distribution. So can we somehow rescale the gradient so that this doesn't happen? Can we have a gradient that points in the same direction, but where the step sizes for different parameters are rescaled so that you take a step that's of the same size in distribution space rather than in parameter space? One of the tools that we can use to try to understand this is to rewrite the gradient descent update as a constraint optimization. Those of you familiar with projected gradient descent or mirror descent will hopefully recognize this. So we can write down the gradient descent as actually a constrained optimization problem where you maximize this linear objective, theta prime minus theta transpose times the gradient, with subject to a constraint that your parameters change by some amount epsilon in a Euclidean distance ball. So this kind of illustrates the problem that you're capping how much your parameters change in terms of Euclidean distance, whereas what you might like to do is actually constrain how your probabilities change in terms of some divergence measure on probability distributions. A very convenient divergence measure to use is actually KL divergence. KL divergence, you can write it as the expectation under your new policy of the log probability of the old policy minus the log probability of the new one. So if you can enforce this kind of constraint, then your steps will affect the policy such that the probabilities change by a fixed amount rather than the parameters changing by a fixed amount. And this could actually address this problem. So how can we do that? Well, it turns out that we can have a pretty efficient method for doing this if we approximate that constraint problem with a second-order approximation of the KL divergence. So if you do a second-order Taylor expansion of the KL divergence around theta equals theta prime, so it's sort of an infinitesimal perturbation, you can write it out as a quadratic form. That's a second-order Taylor expansion. And that matrix F, it turns out to actually just be the Fisher information matrix, which is the expectation under pi of log pi times log pi transpose. And you can actually compute this thing. You can take the very same samples that you use to estimate your policy gradient and also use them to estimate the Fisher information matrix. And that'll give you this matrix F. So what we're trying to do is take a step where the policy probabilities change by a fixed amount epsilon. We're going to approximate this using that second-order Taylor expansion to say that now we're going to cap the change in the policy parameters, but now under this metric F. And we can compute the corresponding gradient ascent step by writing out the Lagrangian. That's how we go from the constrained version to the unconstrained version. And that is just the same gradient ascent step, except that now we multiply the gradient by F inverse. So that's going to take our poorly scaled gradient and turn into this nicely scaled gradient shown in red. So this is referred to as the natural policy gradient. So with natural policy gradient, we pick the step size alpha and then multiply our gradient on the left by the inverse of the Fisher information matrix. Another thing we can do is use a trust region method where instead of picking alpha, we actually pick epsilon, and that gives us an adaptive step size. With trust region policy optimization, we can actually automatically solve for the alpha that enforces a corresponding value of epsilon if we solve F inverse times grad J using a conjugate gradient. So there's a particular trick for doing this that can get us the right step size essentially for free. So for this, see this work by John Schulman. All right, so that's it for policy gradients. Let's review. We talked about how the policy gradient directly differentiates the expected reward. This formalizes trial and error learning, meaning that it makes the good trajectories more likely and the bad trajectories less likely. We can reduce variance by exploiting causality and by introducing a baseline. And we can improve the convergence rate by using a natural policy gradient and also by using an automatic step adjustment with natural policy gradient. All right, let's look at some examples of some policy gradient results. This is the trust region policy optimization method. So this is a natural gradient method with an automatic step size adjustment. It can work with both discrete and continuous actions. So if you can write down your probability distribution for your policy in a way that you can differentiate log pi, you can apply a method like this. And it's relatively easy to use. So it's not the most efficient reinforcement learning algorithm, but because of the automatic step size adjustment and the natural gradient step, it tends to require a bit less parameter tweaking. So if you're just starting off with some reinforcement learning problem and you want to try something quickly, this is often a good choice to get started. And there's some code available in a follow-up paper by Rocky Dwan. All right. So a few suggested readings if you want to learn more about policy gradients. So there are a number of classic papers you can take a look at. So Williams 92, this is actually the paper that introduced the reinforce algorithm. This paper by Baxter and Bartlett talks about the temporally decomposed policy gradient, that gradient that exploits causality. It's actually not the first paper to do this, but I'll mention the first paper to do this later on when I talk about actor-critics. This paper by Peters and Schall has a very nice description of the natural gradient. So if you want to learn more about natural gradients as well as optimal baselines, I'd recommend checking out this paper. And here are some more recent deep reinforcement learning policy gradient papers. This paper covers an important sampled policy gradient estimator. This is the trust region policy optimization paper for which I showed the results before. And this is a more recent work by John Schulman that looks at an important sampled policy gradient estimator that also incorporates a trust region. So if you want to learn about recent policy gradient methods, I'd recommend checking those out. All right, now let's talk about actor-critic algorithms. So let's step back now and look again at this equation for the policy gradient. remember this reward to go thing, which I called Q hat. So the reward to go can be viewed as an estimate of the expected reward if you take an action A in state S. And in particular, it's a single sample estimate here. So you have your sample, you summed up the rewards along that sample, and that's a single sample estimate of an expectation. Which expectation? Well, the expectation under pi of the rewards that you'll get if you start in state ST and take action AT. So can we get a better estimate? A single sample estimator is not very good. It's going to have pretty high variance. It is unbiased in this case, but it will have high variance. If we can somehow compute the true expectation by integrating over all possible trajectories starting in that state in action, then again we'll have a lower variance policy gradient, and we'll be able to learn faster, take bigger steps. So if we had access to the true expected reward to go Q, we could just substitute that in there instead of Q hat, and we'd have a better policy gradient. We can also subtract a state-dependent baseline called V, and of course, just like with average reward, a good choice of that baseline is the expectation under the policy of Q. And I'm using the letter V for this for a reason that I'll explain later. So if we had the true Q and the true V, meaning the true expectation evaluated using an infinite number of trajectories, we'd have a better policy gradient. Unfortunately, we don't have these, but we could do better than a single sample estimator. So by the way, Q minus V, you can call that A for advantage. So a little bit of definitions. So this thing, the expectation of the reward starting in a particular state and a particular action, is often referred to as a Q function. And I'm going to use Q with a superscript of pi to emphasize that it's a Q function for a policy pi. So it depends on pi. It's the expectation with respect to pi. V, which is the expectation of the Q function with respect to the actions, this is called the value function. And again, there's a superscript of pi to denote that it depends on the policy pi. And A, which is Q minus V, is called the advantage function. The advantage function tells you, for a particular action, how much better is this action than the average action, meaning what is the advantage of taking that action. So we can write down sort of our idealized policy gradient as this sum of grad log pi times the true advantage. If we have the true advantage, this will be a good estimator. And the better that we can estimate the advantage, the lower the variance of the policy gradient will be. So this estimator that we had before is unbiased, but it has pretty high variance. If we can fit a function approximator to A, that might introduce some bias, but it will get us lower variance, and oftentimes it'll get us a better policy gradient. So going back to our schematic of a reinforcement learning algorithm, what we've changed is that green box. So we're still going to increment the policy parameters by taking a gradient step, but now, instead of simply summing up the rewards, we'll fit some kind of function approximator to get a better estimate of the advantage in the green box. So we'll actually have something a lot more complex in that green box now. All right, so what are we going to fit, and what are we going to fit it to? We have a few choices. We can fit Q pi, we can fit V pi, or we can fit A pi directly. Here's how we can think about what to fit. Let's take another look at this Q function. Remember that this is the expectation of the reward when you're in a particular state and take a particular action. So the first state and the first action is deterministic. There's no expectation there because that's what you're evaluating. So you can write out the Q function like this. It's the first reward plus the expectation of all the next steps. And that second part, that expectation, that's just the value function of the next state. So you can write out the Q function like this, current reward plus the expectation of the next value. And you can kind of approximate this with just a single sample. It's going to increase your variance a little bit, but that's not too bad. You're going to say the Q function is the reward plus V pi of the next sampled state. And now, if you plug this into the advantage, you get that the advantage is R plus the next value minus the current value. So this suggests that it's awfully convenient for us to just fit the value function. The value function is only a function of the state. It doesn't depend on the action, so there's fewer inputs. So it's going to be a little easier to fit it. So let's just fit V pi. What we're going to do is we're going to build a neural network that takes in the state, outputs an estimate of the value, V hat pi s, and I'm using hat here to denote that it's an approximation. And it's going to have some parameters phi. I'm going to call the parameters phi to distinguish from the parameters of the policy, which are called theta. So V pi is going to try to estimate the expected reward that you get if you start in a particular state and then run your policy. So we need to somehow get some data so that we can fit this value function. But at a high level, here's how the basic kind of batch actor-critic algorithm is going to work. It's called actor-critic because there's an actor of the policy and there's a critic, the value function, that evaluates that policy. Step 1, you sample some states and actions by running your policy, just like before. Step 2, you're going to fit your value function estimator, and I'll tell you what we can fit it to later. Step 3, we're going to evaluate the advantage as the current reward plus the next value minus the current value. Step 4, we're going to plug that advantage into our policy gradient estimator. And step 5, we're going to take a gradient ascent step just like before. So what can we use as the targets for fitting V? Well, we need some estimate of the expected reward. One of the ways we can do that is by using our old single sample estimator. So we can just sum up all the rewards that we got from that state and fit the value function. We're still going to have lower variance because if we fit a value function, that function approximator has some inductive bias, so it's going to generalize a little bit better than just the single sample estimator alone. But we can do actually a little bit better. We can exploit the fact that we have our old value function estimate, and we can actually take the reward that we observed plus the value function of the next state. So this is going to use our old value function estimator to help improve the new one. This can be a little bit less stable because you're basically trying to hit a moving target, but it will further reduce our variance. And then, of course, a convenient loss function to use is something like squared error. So we can just do regression, just running regular stochastic gradient descent with our neural network to fit these target values. And that we do in step 2. Oftentimes, you might not run to convergence every single time. You might run it for some fixed number of gradient steps. All right. Now let me make a little digression to introduce the concept of discount factors. This came up a little bit before, and some of you might have noticed this, that I wrote these target values as being the current reward plus the next value. And you might wonder, well, if we do this over and over again, like the values are getting bigger and bigger, and if the rewards are all positive, this quantity might actually go to infinity. In fact, for some problems, it makes a lot of sense to consider only finite length episodes. If you have, let's say, a robotic manipulation task, maybe for that robot it sort of makes sense that you want to consider just fixed length episodes. You just try the thing, you stop, and you try again. But for some tasks, it makes a lot more sense to consider them as being infinite horizon. They just go on forever. They're cyclical, periodic. So for these tasks, it's very convenient to think about infinitely long trajectories, but now you have this problem that your values will go to infinity because you're summing over infinitely many potentially positive rewards. So there's a small fix that we can use to address this issue. What we're going to do is we're going to say that getting rewards sooner is just a tiny bit better than getting them later. So we're going to do this by introducing what's called a discount factor, which is a little constant that multiplies the value in this estimator. So we're going to take the current reward plus some constant between 0 and 1 times the next value. And a value of 0.99 works pretty well for this. This just says that getting a reward sooner is better than getting it like a year from now. It turns out that mathematically, this makes perfect sense. All it does is modify your MDP in a very particular, well-structured way. So gamma changes the MDP as following. If you have, let's say, a 4-state MDP, four states and you can transition between them, if you add this discount factor gamma, that's equivalent to adding a 5th state that is an absorbing state. It's like a death state. Once you get there, you get no more rewards. You always get a reward of 0. And your probability of moving into that state at any given transition is just 1 minus gamma. So every time you choose an action, there's a small probability, a probability of 1 minus gamma, that you will die and never see any rewards again. That probability is small, so you'll still be a relatively happy individual, but it'll cause you to favor rewards sooner rather than later. And that's, of course, true for us. We know that we're all mortal, so if you have $1 million, you don't want to wait 300 years to spend it. All right, so that's discount factors. And now I've just plugged that discount factor into the batch mode actor critic algorithm in step number 3. We can also derive an online version of the actor critic algorithm. We couldn't do this for policy gradients before because for policy gradients we need to sum up all those future rewards, but we can do it for actor critic. So the setup is very simple, but now it's going to be fully online. You take one action with your policy and you record the state, the action, the next state that you got, and the reward. You're going to update your value function estimate with one gradient step on just that r plus gamma vs prime. Then you're going to evaluate the advantage of that transition. Then you're going to compute your policy gradient estimate, again using just a single sample. And then you'll increment your policy parameters. And then you'll repeat. So now this is a fully online actor critic algorithm, meaning every single step that you take in the environment, you can improve your policy. We couldn't do this before with policy gradients because we couldn't evaluate the advantage using just a single step. Now, in practice, this is not actually a very good algorithm because if you're optimizing a big neural network, this is essentially a mini batch of size 1, which is not very good. You can get a much better algorithm if instead you have multiple workers collecting multiple transitions in parallel. So step 1 is actually take actions multiple times in parallel in different simulations, for example, get multiple states, get multiple targets, update using that as your mini batch, and then update the gradient using the same mini batch. Another thing you can do to improve actor-critic algorithms is design better estimators for the advantage. So the particular estimator that I showed here, this is using the estimated value for the very next step. You can actually blend between this kind of maximally bootstrapped advantage estimator and the maximally Monte Carlo estimator where you just sum up the rewards. You can actually blend between them to have something that trades off bias and variance, because this estimator has low variance but higher bias, because if your value function is wrong, the estimate might be completely off. If you sum together the rewards, that is unbiased, but it has higher variance. And you can actually blend between them, and to learn more about that, check out this paper by John Schulman. As far as the architectures that you can use in an actor-critic algorithm, a very standard kind of default choice is to have two neural networks, one neural network for estimating the value, and a separate neural network for the policy. This is simple and actually quite stable because the two networks are learning completely separately. They're not affecting each other. But there are no shared features between the actor and critic. If you believe that the features that you need to estimate your value are somehow related to the features that you need to estimate the policy, then you can also combine these into a single network with two heads, one for outputting the value and one for outputting the action distribution. So let's review. We talked about actor-critic algorithms, where there are two neural networks, or one neural network with two heads, one of which is the policy, and the other one is the value of that policy. So that's the actor and the critic. The actor predicts the action from the state, and the critic evaluates the state. The connection to policy gradient is that this is just policy gradient with a function approximator for the advantage. There are multiple ways to estimate the advantage, and it can be batch or online. Here are a few examples of actor-critic algorithms. This video is from a paper on something called the generalized advantage estimator. This is an actor-critic algorithm, a batch mode actor-critic algorithm that blends Monte Carlo and fully bootstrapped advantage estimates. So it's batch mode. This is a video from a paper that introduced an algorithm called A3C. A3C is a fully online parallelized actor-critic algorithm. And there's also a single network that has two heads, one for the actor and one for the critic. And this video that you're seeing is actually a recurrent actor and critic. All right, a few suggested readings. So here are some classic papers on actor-critic algorithms. This is a paper that talks about actor-critic algorithms and also talks about the temporally decomposed function policy gradient approximator. Some more recent deep reinforcement learning actor-critic papers. This is the A3C paper, which has the parallel online actor-critic. And this is the generalized advantage estimation paper, which talks about a batch mode actor-critic. And this is a more recent paper that actually talks about using a control variate that depends on the state and the action, which is trained as a critic. So it's actually used as a critic not as directly as the estimator of the advantage, but as a baseline, as a control variate. And that gets you an unbiased actor-critic algorithm. All right, so the last topic that I'll discuss before the break is direct value function methods. So can we omit the policy gradient completely? So far, both of the methods that I described, policy gradients and actor-critic, they still at their heart have this policy gradient kind of gradient ascent procedure. But maybe we can just get rid of that and have only a critic. So let's recall some definitions. The Q function is the expectation of the total reward under your policy. And if you take the action that the Q function thinks is best, that's the best action from that state if you then follow the policy pi. So it's at least as good as any action that you would sample from pi, right? Any action that you sample from pi has to be as good or worse than this max, regardless actually of what pi is, provided that Q is the Q function for pi. So how about we just forget about policies and let's just do this. Let's just take actions according to the max of for the Q. Well, instead of fitting V pi, we'll fit Q pi and just take the max. So the corresponding policy just looks like this. The probability of an action in a given state is just 1 if that action is the argmax of your current Q function estimate and 0 otherwise. And then this action this new policy, pi prime, has to be at least as good as pi. And it's probably better. So the resulting algorithm is going to have this structure. In the green box, instead of fitting V pi, we'll now fit Q pi, the same way that we fit a V pi. It's just that now it's a function of states and actions. And in the policy improvement box, we'll just set pi to be this new pi prime. Okay, so that's kind of the general intuition behind purely value function-based methods. But I'll first back up a little bit and talk about a method called value iteration. It's still going to fit V, and then I'll come back to this notion of fitting Qs. So this is dynamic programming, basically. So if you remember, the Q function is the current reward plus the expectation of the next value. So if we know the dynamics, it's actually enough to just compute the value, because if you know the dynamics, you can always evaluate the Q function as the reward plus the expectation of the next value. So let's go back and evaluate the value for now, because this will be a little simpler to deal with. It's the expectation under pi of the Q function. And what is pi? Well, pi is this thing, the thing that we had before. So it's 1 if A is the argmax and 0 otherwise. So that means that the expectation under this very degenerate distribution is just the max with respect to the action of Q. So we'll fit the V as the max of Q, and that gets us the following algorithm. In the green box, we estimate Q's as being the reward plus gamma times the expectation of the next V, and in the improvement box, we set V to be the max with respect to actions of Q. And this is the value iteration algorithm. So you just evaluate your Q's at all of the states and actions, and then set the V to be the max. The problem is that we need to know the transition dynamics, but we'll fix this problem shortly. We also need to represent V. This gets a little tricky. So if we represent V, for example, as one big table with an entry for every possible state, that is guaranteed to converge. It's fixed point iteration. It's a very good algorithm. The trouble is that it requires us to enumerate all possible states. So if your states are, for example, pixels in an image, this is like 255 to the third power to the 200 by 200th power. This is more than the number of atoms in the universe, and it's completely intractable. So this is called the cursive dimensionality. So in large state spaces, we'd have to use some kind of function approximator, like a neural net. Just like before, it maps from states to the values, has some parameters phi, and that gets us the fitted value iteration algorithm. So the loss here is just the difference between V phi of S and the max of the Q function. And what you can do is you can sample some states and actions, evaluate the target values as the reward plus the expectation of the next value, and then set phi to be the parameters of the neural net that minimize this error. So this is fitted value iteration. You still have to know the dynamics, though. So we can get rid of this as following. Notice that the place where we need to know the dynamics is just this. We need to know the outcomes for different actions in order to perform this maximization. So what we can do instead is actually just learn Q, as I mentioned at the beginning. Instead of learning V pi, let's learn Q pi by directly fitting this RSA plus gamma times the expectation of the next value. And remember that the next value is just the max over the actions. So this is the fitted Q iteration algorithm. Compute your targets, update the phis, and the expectation over the V's will estimate using one sample from the transition and the policy which we know, which is the max with respect to A of our Q function. So we'll set the target values to be RSA plus gamma times max with respect to A prime of Q phi S prime A prime. And now we're just fitting Q phi. We're not fitting V at all. In fact, V wouldn't even appear in here. This doesn't require simulating any different actions. It doesn't require knowing the transition dynamics, which means that we can do it in a fully model-free way. So it works. It even works actually for off-policy samples, unlike actor critics. So we're actually making no assumption that the samples here came from any particular policy. There's only one network. There's no actor at all. So there's no high variance policy gradient. The objective is just a regression objective. Unfortunately, there's actually no convergence guarantee for nonlinear function approximators for this algorithm, which is a little bit sad. Although if we're careful in tuning our parameters, we can get this to work in many cases. We can also derive an online version of the Q-learning algorithm. The online version, very similar to the fitted Q iteration algorithm. You just take some action, AI, and observe a transition Si, AI, Si prime, Ri, and then you just compute the gradient for that single sample. So you just take your current value of Q minus the target value, which is Ri plus gamma times the max with respect to the action at the next state, and then you multiply that by dq d phi, so you just backpropagate that error, and then you update your Q function network. And again, this is off policy, so there are many choices for which policy you can use to sample that transition. A very popular choice is what's called an epsilon greedy policy. So here you take the best action with probability of 1 minus epsilon, because if you always take the best action, then you'll basically always do the same thing. So this gives you a little bit of exploration, a little bit of randomization. You take it with probability 1 minus epsilon, and with probability epsilon divided by the number of actions minus 1, you take some other, you take another action. So probability epsilon, you take a random action that's not the best. Probability 1 minus epsilon, you take the best action. This is called epsilon greedy. Now, in practice, this has a number of challenges. First, you're basically doing gradient descent again with a single sample mini batch. That's already kind of a bad idea, but it's even worse than that because you're collecting these samples one at a time by acting in some sequential decision process, which means that the samples are temporally correlated. So not only are you taking single sample gradient descent steps, you're actually taking gradient descent steps on data points that are not decorrelated, which means that if you're in a particular part of the state space, you're walking around there, your Q function will badly overfit to just that part, and then you go somewhere else and it'll badly overfit to that new part. So this actually breaks a lot of the nice properties of gradient descent, stochastic gradient descent. The other issue is that your target values are always changing. So it's a regression objective, but it's a regression objective where the thing that you're regressing onto keeps changing out from under you. So this is a recipe for disaster. It causes some pretty bad instability issues, and of course it doesn't converge. And Q-learning, just to clarify any misconception, it's not actually gradient descent. It's not gradient descent because the target value depends on the parameters that you're learning, but you're not differentiating through that. So the usual properties of gradient descent don't really apply here. There is a better Q-learning algorithm that we can derive. It's still not guaranteed to converge, but it works a lot better in practice. You take some action, AI. This is, by the way, from a paper by Vlad and collaborators from DeepMind. You take some action, AI, and you observe a transition SI, AI, SI prime, RI, and then you add it to what's referred to as a replay buffer, a buffer of data that you're going to pull from later to update your Q function. Then you're going to sample a mini batch of transitions from that replay buffer, and then you're going to compute target values for every single sample in that mini batch by using a target network, and I'll mention what the target network is shortly. So not the network you're learning right now, but a slightly different network, a target network. You're going to use that to label all these transitions with their reward plus gamma times the max of their Q value. And then you're going to update your parameters now with this entire batch of data. So now you're using multiple samples. The samples are sampled uniformly at random from your replay buffer, so that helps to decorrelate them. And you're actually using this target network. The way that you update the target network in step 5 is you either copy over the parameters phi into phi prime every n steps, where n is big enough to stabilize your algorithm, or you can also do a Polyak average. You can basically have this weighted average where at every step you multiply phi prime by tau, where tau maybe is 0.99, plus 1 minus tau phi. So somehow you're slowing down the updates to phi prime so the target values don't change as rapidly. So these two modifications go a long way towards helping stabilize Q-learning. It's still not guaranteed to converge. But if you tune the parameters carefully, you can actually get pretty good results out of that. And the nice thing is that these transitions, you're actually recycling old transitions that you saw. So that makes this algorithm actually quite a bit more efficient than policy gradients. So here's, okay, so that's the Q-learning algorithm. This is actually the DQN algorithm proposed in the Nature paper on playing Atari games. You can also do Q-learning with continuous states, and there are a couple of ways to do this. A very simple way to do, so what's the problem with continuous states? The problem with continuous actions. The problem with continuous actions is the max. So you have to maximize your Q function with respect to some continuous value, which means that you can't just enumerate all possible actions and take the best one. There are a couple of ways that you can get this to work. One relatively easy one is to use a function class for Q that is easy to optimize with respect to A. A few possible choices here. One really simple one is to just use a Q that is quadratic in the action. So this is from a paper by Shishan Gu called the NAF architecture, where your Q function is some quadratic function where the parameters of that quadratic are outputted by a neural net. It's a more restrictive function class. You can't represent all functions of the action that way, but you can maximize it very easily with respect to the action. Another choice is to actually learn an approximate maximizer. So this is the method proposed in the DDPG paper, Continuous Control with Deep Reinforcement Learning by Lillicrap et al. And here, what you can do is you can actually train a second neural net called mu, which gives you an action that is trained to be the argmax of Q. So mu is basically trained by pushing gradients through Q. You write down basically the Q function, differentiate with respect to the actions, and push those gradients through mu. And then, instead of actually evaluating the max analytically somehow, you just take the Q function of S comma mu of S. And this is sometimes referred to as the deterministic actor-critic, although it's really an approximate version of Q-learning, because actor-critic algorithms involve having a policy gradient. All right, so let's review. I talked about value-based methods. These methods don't learn a policy explicitly. They just learn a value function or a Q function. If we have a Q function, then we have a policy, because we can simply take the actions that maximize the Q function. Value-based methods can be batch or online. They are not in general guaranteed to converge, but with things like replay buffers and target networks, we can help stabilize Q-learning algorithms, and with a little bit of parameter tuning, empirically we can often get convergence. And then there's some approximations that we can make to also handle continuous actions, which in the general case are not entirely trivial. All right, let's look at a few examples of Q-learning. So this is the DQN paper by Vlad and Yi from first published in 2013. This is Q-learning with convolutional neural networks. I use a replay buffer and a target network to stabilize Q-learning, but otherwise it's basically the Q-learning algorithm that I presented using a convolutional neural network to represent the Q function without any explicit policy and just taking the max over the actions. This is a video from a paper on a continuous variant of Q-learning. This is using NAF, that quadratic estimator that I showed before, and this is showing a robot learning to open a door. It's actually two robots learning to open a door together in about 2.5 hours. This uses NAF, which is, as I mentioned, quadratic in A, and it learns this in about 2.5 hours. All right, a few suggested readings for Q-learning. So this is the classic paper by Watkins that actually introduces the algorithm. Another paper that might be interesting to check out, this is a work by Reed-Miller that introduces a fitted Q iteration algorithm. So this is using a neural network to fit the Q function in batch mode. And then some more recent deep reinforcement learning papers. This is a paper by Lang and Reed-Miller where they actually use a autoencoder to embed image observations into a low-dimensional state and then do Q-learning in that embedded state. This is the work by Vlad and Yi that I showed before. This paper, called Deep Reinforcement Learning with Double Q-learning, introduces a very effective trick that greatly improves the performance of Q-learning. So if you're interested in implementing the algorithm in practice, I highly recommend checking that out. This is the paper on continuous actions using a learned maximizer that I discussed before. And this is the paper on using the NAF estimator with quadratic Q functions quadratic in A. And lastly, this paper introduces what's called the dueling network architecture, which is another design for a neural network architecture for Q-learning that tends to work pretty well. All right, so before the break, let me make a few concluding remarks. For the algorithms that I talked about before, they have various trade-offs. One of the things that's very different between these different algorithms is their sample complexity. So I can show you a little kind of analysis that I did by kind of looking at the results reported in different papers and trying to make sense of which ones are more or less efficient. Now, take this analysis with a grain of salt because different works test on different benchmarks with different parameters and so on. But at a very high level, we can kind of guess at the efficiency of these algorithms roughly like this. The most inefficient typically are gradient-free algorithms. I didn't talk about these in detail, but these are things like CMAES or natural evolutionary strategies. By the way, efficient doesn't necessarily mean good or bad. This is just how many samples they require in the real world. More efficient than that would be fully online methods, methods that are on policy but have to run online like A3C. Batch mode policy gradient methods typically require less samples than that. Methods that can use a replay buffer typically require even less samples because they can make use of all that older data. They can recycle the older data. Model-based methods, which Chelsea will talk about in the second half of the tutorial, tend to be more efficient. And then shallow reinforcement learning methods are typically even more efficient, although, of course, more restricted in the kind of problems they can be applied to. And actually, the difference between these different levels tends to be about 10x between each one in terms of sample efficiency. So I won't cover the slide in great detail, but you can find it on the website, which basically picks out the results reported on what's called the cheetah benchmark. This is a standardized, a reasonably standardized task that involves teaching a little simulated cheetah to run. Unfortunately, different versions of this task are a little different, so these numbers are not directly comparable, but up to an order of magnitude, this kind of makes sense. So A3C reports results on this that take the equivalent of about 15 days of real time. The simulator is much faster than real time, so it typically takes less than that computationally, but if it were running in real time, 15 days. Batch mode policy gradient like TRPO takes the equivalent of about 1.5 days of real time. Methods like DDPG take about the equivalent of about 3 hours of real time. And actually we found that if we run them on a real robot, that's about how long they take to learn some manipulation skills. So that 3-hour figure is probably pretty reasonable. Model-based algorithms tend to take on the order of about 20 minutes of real time. Of course, they also introduce some additional assumptions, so you have to be wary of that. And then shallow reinforcement learning algorithms, of course, tested on different tasks, take even less than that. On simpler tasks, they can be as few as a couple of minutes or even less than a minute. So there are big differences in sample efficiency between these different methods. So which RL algorithm should you use? Here's sort of a very coarse, high-level flow chart that you can use. Now, take this with a grain of salt, of course. It depends very heavily on the particulars of your problem. But when I'm tackling a particular reinforcement learning problem, one of the first questions I ask is, are you learning in a simulator? So do you have access to a simulation of the system, or do you have to actually learn directly in the real world? If you're learning in a simulator, the second question you can ask is the simulation cost negligible compared to training cost? Meaning, does it take more computation to do one backpropagation step through your network than it does to simulate one time step in your simulator? So if your simulator is very cheap, then you'd like to use an algorithm that is not efficient. So these algorithms at the top right here might actually be preferable in this case because simulation is cheap. You don't care how many samples you need. So in that case, good choices are policy gradient methods, including online methods like A3C or batch mode methods like TRPO, because they're going to require less computation time, even if they take more samples. And this is a video that was generated with TRPO. If simulation cost is not negligible, then you might want to use a more efficient algorithm that actually uses a replay buffer to recycle old experience, like QProp, DDPG, or NAF. But if you have access to a simulator, another question that you should ask is, if you have a simulator, can you compute gradients through that simulator? And if so, do you really need model-free RL? Because if you can compute gradients through your simulator, you can do gradient-based optimization, and that can produce some really good results. This is actually a paper by Igor Mardac that illustrates a variety of locomotion skills learned by computing gradients through a simulator, which, of course, you wouldn't do in model-free RL, but if you have a simulator, then you can. If you're not learning in a simulator, then the question to ask is, how patient are you? If you are impatient, then maybe you should investigate using a model-based algorithm, which is typically going to be substantially more efficient if you can make sure that your problem meets sort of the assumptions of the model-based algorithm that you use. And these can be used to learn a variety of real-world robotic skills. If you're a bit more patient, or if the problem you're trying to solve doesn't fit into the assumptions of a model-based RL algorithm, then QProp, DDPG, or NAF might be good choices. And these have also been demonstrated to work on real-world physical systems. Okay, so at this point, we're going to take a short break. The break will be, let's say, about 4 minutes long, and then we'll resume after the break with more advanced topics. Well, so the trouble with theoretical justification is that even with experience replay, convergence is not actually guaranteed. So it's, to the best of my knowledge, and I'm not aware of any work that actually shows a theoretical benefit to experience replay, there is a very, like a formal one. There is kind of a natural intuition for why it helps, because you, can I do this afterwards? Okay. Because you're essentially decorrelating the samples that you use for the gradient step. So from the standpoint of stochastic gradient descent, it makes a lot of sense that using experience replay would help. But because formally it's still not guaranteed to converge, it's hard to say anything very formal about it.
The important thing is to relate samples.
That's the best guess that people have about why it's important, yes. But again, it's like there's only so much you can say if you can't even prove convergence of your algorithm.
Okay, thank you.
Sure, they're pretty quick. From what? So typically the main, typically one of the things that you need for most of the algorithms representing is for the reward to depend on the state in the action. So if the reward depends on, let's say, history, if it's still good in many cases, so oftentimes, you can use any function. Yeah, you can use any function. But if it's a function of the state of the action, if it's a function of the entire trajectory, you can still use it as some loss gradient algorithms. But you can't use it, for example, for Q. You don't need a gradient. None of the methods that I described before. Actually, maybe we can take the questions after this talk. So, I'm sorry.
I'm good.
One line. No, sorry.
To sign the
yeah,
release form?
we'll sign it afterwards. You can wait.
I signed mine. Okay, I think I'm all set up. I just turned off my screen, but I'm going to keep it open so that
Okay.
maybe I'll
Do you want to test it? We have about.
I tested it.
Okay.
Cool. So we're a bit over.
How much?
It's like, so at the end of the break,
So we'll start at 2:17.
We'll be 7 minutes over.
Oh,
We're supposed to be 10.
Yeah, 7 minutes. Okay. I need a break because I can't talk for more than an hour.
There were parts that took longer.
like a total of like 10 minutes over.
And I'll come up. What is your last slide?
It is the papers.
So I'll like stand up.
Yeah. Okay, so please be seated. We're going to continue shortly. Okay, let's continue. So in the second half of this tutorial, we'll talk about some more advanced topics. I'll cover something called soft optimality, which discusses a relationship between reinforcement learning and inference. And then Chelsea will talk about inverse RL, model-based RL, and some frontiers and open challenges. So let's start with the first topic. The question that I'm going to discuss next is reinforcement learning inference in a graphical model? And I'll talk about the theoretical foundations behind this first, and then I'll discuss a few examples and why we should care about this. So we saw before that in reinforcement learning, we can draw a graphical model that describes how states relate to actions. We can also put observations in here. So last time I showed this picture, it had observations. For now, I won't worry about observations. So in this graphical model, the next state is determined by a probability distribution that's conditioned on the current state in action. Now, if we want to somehow fit all of reinforcement learning into a graphical model, we need to incorporate rewards into this picture somehow. So how can we incorporate rewards? Well, what we can do is we can add another variable to this graphical model, which I'm going to call O for optimality. And this variable captures how good a state action tuple is. And then what we're going to want to do is we're going to try to somehow build this graphical model and design a distribution for O such that when we do inference, let's say we'll have binary O's, we'll set them all to true, such that when we do inference to say all the optimality variables are true, we should recover good trajectories. So what's the probability of a trajectory under this graphical model? Well, we need to define the probability of the optimality variables. So what we're going to try to do is define them such that the probability of a trajectory, given all the O's being true, somehow gives the highest probability of the best trajectory. So we'll define the probability of these binary O variables as following. The probability of OT given ST and AT is going to be proportional to the exponential of the reward for that state in action. And we'll make sure, and we'll add some assumptions to make sure that this is actually a valid way to define the probability of a binary random variable. If we define P of O given SA like this, then we can write down the probability of a trajectory given all the optimality variables as the probability, as their joint probability divided by the probability of optimality. This is just the definition of conditional probability. And this is proportional to the probability of the trajectory times the product of the probabilities of all the binary optimality variables. Now, the product of exponentials is the exponential of a sum, so that means that this comes out to just the probability of the trajectory occurring naturally, basically it's probability under the dynamics, times the exponential of the sum of rewards. If we assume that our dynamics have some regularity to them, for example, in a discrete environment, maybe our transition is, we transition to some state with high probability and all other states with some low probability. If that term P of tau is relatively flat, then this is going to be basically dominated by the exponential of the reward. So it'll say that the most rewarding trajectory is the most likely under this distribution, and as they have lower reward, they become exponentially less likely. So in particular, if you take your reward function and you increase its magnitude all the way to infinity, basically you multiply by some really big factor, then that second term in the product will completely dominate, and it'll be a very sharp exponential, which means that only the best trajectory will have non-zero probability. So you can basically shoehorn your reinforcement learning problem into a probabilistic graphical model in this way, and the most likely trajectory will be the optimal one. Okay, so that's the high-level design of this probabilistic graphical model. Now let's dig into it in a little bit more detail. So here at the top, I'm just going to keep the definitions just to remind you: the probability of optimality given the state in action and the probability of a transition. These are the things that we have. And there are three kinds of inference problems that we might want to solve in this kind of graphical model. The first is to compute backward messages, which is the probability of optimality at all time steps from now until the end, given the current state in action. And as I'll discuss later, this has a very close relationship to things like Q functions and value functions. The second question that we often want to answer about these kinds of graphical models is, can we compute a policy? Can we compute the probability of an action given a state and all of the optimality variables being true? Basically, the distribution over actions in the case of optimality. And the third question that we often want to answer is how can we compute forward messages, the probability of a state given all the previous optimality variables being true. This is going to be useful if we want to compute state distributions for optimal behavior. Okay, so let's start with the first question, computing the backward message. The derivation here will be a little bit dense, but when I'm done, you'll see that this actually has a very close relationship to some of the value function and Q function ideas that we presented in the first half of the tutorial. So the backward message is defined as the probability of optimality from now until the end, given the state in action. We can write this as an integral over the next state. So this is just marginalizing out the next state. And that distribution we can break up to be the probability of optimality for all the time steps at t plus 1 until the end, times this transition term, times the reward term. So this term we know, this is just the probability of optimality at a single step. This term is just the transition dynamics. And this first term, that's the complicated term. So we need to do a little bit more derivation to figure out what that is. That term, you can introduce the action at the next time step, and you can write it as the probability of ot plus 1 through t given the next state in action, times the probability of the next action given the next state. This part, this is simply the backward message at the next time step. So that suggests that we're going to have something that looks like a dynamic programming algorithm. And this second term basically tells us which actions are likely a priori. If we assume that in the absence of optimality we're just going to act randomly, then all actions are about equally likely. So we can say that the second term is just a constant. So we can just assume uniform for now. In general, it might be something else, and that leads to a family of really interesting algorithms that have what's called passive dynamics. But for now, let's just assume it's uniform, and we can just ignore it. So now, with this derivation, we've shown that we can compute these backward messages using a simple dynamic programming algorithm. So we start at the end, and we compute the state action backward message as the probability of optimality at that time step times the expectation of the state backward message at the next time step. And the state backward message is computed as simply the expectation under the action of the state action backward message. Okay? So this is the algorithm for computing the backward messages. And this is just obtained based on what we know about probability distributions. This is just inference in a graphical model. But now let's take a closer look at this backward pass. There's something interesting going on here. Let's introduce a little bit of notation. Let's say that v of s is equal to log of beta s. And I'm intentionally using v because this is going to look a lot like a value function. And let's say that q of s comma a is equal to log of beta s comma a. Now, let's look at this operation where we compute the state backward message. If we do this in log space, that just amounts to saying that v of s is equal to the log of the integral of the exponential of q of s comma a. So I've just substituted v's and q's for log beta and log beta s comma a. If q gets bigger and bigger, this log of the integral of the exponential will be dominated by the biggest q. So this is a lot like saying that v is going to be the max with respect to the actions of the q values. But if q values are small, then it's kind of a soft max. So it's going to break ties by averaging them. So it's a little different. Let's look at this first term. We can write it out in log space like this. The q value is equal to the reward plus the log of the expectation of the exponential of the next value. Well, let's now look at the value iteration algorithm. It looks kind of similar. The q value is the reward plus gamma times the expectation of the next value, but not exactly the same. In the deterministic case, where the states transition deterministically, the q value is just r plus the next v, and that's the same as in value iteration, which is interesting. In the non-deterministic case, it's not quite the same. The way in which it's different is actually kind of peculiar. It's kind of optimistic, meaning that if there's some value for a lucky transition that's really good, that's going to dominate this expression. So if you're driving along the side of the cliff, and sometimes you fall off the cliff and sometimes you don't, the times when you don't fall off will actually dominate this expression. That's actually not very good for reinforcement learning. You don't want to be optimistic with respect to stochastic dynamics. You want to actually consider the average case. So it turns out that you can write a more complex probabilistic graphical model, which I won't present here because it's a little bit involved, but it's discussed in more detail in this work by Brian Ziebart called Modeling Interaction via the Principle of Maximum Causal Entropy. And in that more complex graphical model, it actually turns out that you actually do get q's that are equal to r plus the expectation of the next value. This is a better way to do it. So what we've shown here on the slide is that when you do inference in this graphical model, with a few little modifications, you actually get equations that look quite similar to computing Q values and value functions, where the state action backwards message looks a lot like a Q function, and the state backward message looks a lot like a value function. All right, now let's look at the second inference problem, the problem of computing the policy, AT given ST, comma, O1 through T, meaning the distribution over actions for a given state given optimality, given that you're acting optimally. So that's going to be our policy, pi A given S, and we can write it like this. We can first discard all the optimality variables before T, because we know that the state, you're conditionally independent of all the past optimality given the state. So we can write it as AT given ST, comma, O little t through big T, instead of 1 through big T. Then we can apply the definition of conditional distributions to write out like this, P of A comma S given O divided by P of S given O. And now we can apply Bayes' rule to both the top and bottom of this ratio. So here I've applied Bayes' rule to write it as P of O given AS and P of O given S. This term cancels out because it's on both the top and bottom, and you're just left with a product of two ratios, P of O T through big T given AS divided by P of O T through big T given S, times P of A comma S divided by P of S. Recall that the backward message is exactly the top part of this ratio, and the state backward message is the bottom part. And the second ratio is just P of A given S. That's the prior probability of an action, which, as we discussed before, is just a constant. So that means that you can write out this policy simply as the ratio of the state action backward message divided by the state backward message. Okay, that's kind of interesting. Now, let's remember this relationship between Q functions, value functions, and backward messages. If the policy is the state action backward message divided by the state backward message, and the value function is the log of beta S, and the Q function is the log of beta S comma A, then the policy is actually the exponential of Q minus V, and that's just the advantage. So the policy is equal to the exponential of the advantage. That seems very natural. That means that the best action according to your Q function is taken most often, and the other ones are exponentially less likely. So this actually completes the derivation of what's sometimes called maximum entropy reinforcement learning or stochastic optimal control, where you're using this inference formalism to derive policies, because now you have a policy and that's what you're after. There are a few variants of this approach. You can actually derive a discounted version of stochastic optimal control, where you have the reward plus gamma times the expectation of the value, so that's just the same as in value-based methods. You can also introduce an explicit temperature, so you can say that V is equal to alpha times log of the integral of the exponential of 1 over alpha times Q. So as alpha goes to 0, this actually reduces to standard hard optimality, so the standard kind of formulas of reinforcement learning. But for larger values of Q, larger temperatures, you actually get the soft optimality. And there are a few other variants that I'll discuss when I talk about related literature at the end. The last inference problem that you might want to study is finding the forward message. This will seem a little bit peculiar, but it'll be very important later on when we talk about inverse reinforcement learning. So the forward message is what you're going to use to figure out the probability of being in a particular state given optimality at all states. The forward message itself is defined as the probability of a state given optimality at all previous states. The first forward message is typically just your prior probability of being in a particular state. And you can compute subsequent forward messages recursively as following. First, we are going to put the previous state in action into the integral and marginalize it out. Here, this term is just the transition, this term is the previous forward message, and this middle term is the hard one. So the middle term you can write out using, again, Bayes' rule as the probability of optimality at that step given the state in action times the prior probability of the action divided by some constant of proportionality. So that allows us to basically evaluate the forward message at this point. And if we then want to find the probability of being in a particular state given optimality at all time steps, we can write it out like this. It's the probability of a state comma optimality divided by optimality. That's from the definition of conditional distributions. We can break up that top part to be the probability of optimality at all future states given the state times the probability of a state and all past optimality. So the first part here is just the backward message. And the second part, you can break it up into the probability of a state given past optimality times the probability of optimality. The probability of optimality doesn't depend on the state, and the other term is simply the forward message. So that means that the probability of being in a given state, given optimality, is just proportional to the product of the forward and backward message. And of course, those of you that are familiar with hidden Markov models will immediately recognize this as exactly the same as what you get when you do inference in hidden Markov models or common filters and so on. So we can use the backward message and forward message to figure out how likely we are to be in a given state, given that we're acting according to the soft optimality rule. All right, so in summary, I discussed how probabilistic graphical models can be used to express optimal control methods as inference in this graphical model. Control here is basically equal to inference. It's similar to HMMs and extended common filters. And it's actually very similar to dynamic programming, value iteration, and Q-learning and so on, but soft. So we can actually do Q-learning with soft optimality. So the standard Q-learning algorithm basically updates the parameters according to the gradient of the Q function times the difference between R plus next V minus Q. And the target value in regular Q-learning is given by a hard max over the next action. In soft Q-learning, exactly the same thing, but the target value is now given by a soft max, meaning the log of the integral of the exponential of the Q. Otherwise, everything stays exactly the same. The policy, in this case, we can choose to be the exponential of the advantage, so that all makes sense and works out quite nicely. So the corresponding soft Q-learning algorithm, again, looks exactly the same in almost all regards to the standard Q-learning algorithm, with the only difference being that the target values are now computed using the softmax, and when you act in the world, you should act according to this exponential advantage policy. We can also compute policy gradients with soft optimality. So it turns out that when your policy is the exponential of the Q function minus the value function, what the policy actually optimizes in that case is the expectation of the reward plus the entropy of the policy. This is why this is sometimes referred to as maximum entropy reinforcement learning. So it's a little bit of a different notion of optimality, but standard optimality is a special case of this because as you increase the magnitude of the rewards, the entropy term has a lower and lower proportional weight, and the rewards dominate. So you can get hard optimality as a special case of this just by having very large multipliers on your rewards. The intuition for why this is maximizing entropy is the following: that if your policy is proportional to the exponential of the Q value, that means that the policy is basically minimizing the KL divergence between itself and this distribution that's 1 over z times exponential of Q. And when you minimize KL divergence, what you're really doing is you're minimizing the expectation. This should be negative Q, the expectation under pi of negative Q minus the entropy. So that's why choosing your policy to be the exponential of Q is actually maximizing the entropy of your policy. So this is often also referred to as entropy regularized policy gradient. Very often it's actually used to combat this kind of premature entropy collapse problem where your policy will become more and more deterministic very quickly and as a result lose its ability to explore. This often happens, for example, if you have a reward function that penalizes taking large actions in continuous control. It's very tempting for the policy to just reduce its variance and stop exploring. And this entropy regularization tends to combat that. And it turns out that it's actually very, very closely related to soft Q learning as analyzed in these two papers. All right, so why should we care about this? What are some of the benefits of soft optimality? Well, it can improve exploration and prevent your entropy from collapsing in policy gradient methods. It's a principled approach to break ties, so if you have a few actions that are all about equally good, this method will actually choose all of those actions instead of arbitrarily picking one that's a little bit better. It can reduce to hard optimality as the reward magnitude increases, so hard optimality is a special case of this. And it turns out that this is actually a very good model for modeling human behavior, as Chelsea will discuss later when she talks about inverse reinforcement learning. Soft optimality also allows you to actually have compositionality. So what I mean by this is that if you have two Q functions for two different reward functions, simply adding those Q functions together is not the optimal Q function for the sum of those rewards under conventional hard optimality. But under soft optimality, Q functions are actually the logarithm of the probability distribution of the action. And if you multiply together two trajectory distributions, that's the same as the exponential of adding together their logarithms. So I won't go into this formally, but it turns out that adding Q functions under soft optimality can actually allow you to find the optimal Q function for a sum of rewards. All right, let's review. So I talked about how reinforcement learning can be viewed as inference in a graphical model, where the value function is the backward message, and this corresponds to a policy objective which says to maximize reward and to maximize entropy. Basically, you're trying to find the most random policy that still gets good rewards. But the bigger the rewards are, basically if you put a multiplier on the rewards, the less the entropy matters, so this can be reduced to hard optimality. I talked about soft Q learning, which is an algorithm that uses the soft optimality in a Q learning algorithm, and I talked about how this can be fitted into the framework of policy gradients by adding that entropy regularization term. Here's an example of a soft Q learning algorithm. This will actually be presented in the main conference. So here what you're going to see is the policy learned with soft optimality for a quadrupedal robot that is rewarded only for running fast, regardless of which direction it's running in. On the left, you'll see a deterministic algorithm. This is actually DDPG from before. And on the right, you'll see soft Q-learning. And DDPG just has additive noise. So here what you can see with soft Q-learning is all these little quadrupedal robots, they all run in different directions. So it's actually learning a very diverse policy because it's maximizing entropy and at the same time getting them to run fast. Now, why is this useful? Well, it turns out that if you have this maximum entropy policy, you can use it as a very good initialization for then solving a new, more constrained problem. So here we just took that policy from soft Q-learning, that's the one on the far right, and used it as initialization in a new setting where the quadrupedal robot has to run in a particular direction. And because that policy already knows how to run in all sorts of different directions randomly, it's very quick to then adapt to run in a single direction. All right, a few readings about soft optimality. The framework of soft optimality was introduced actually independently in a number of different papers. One line of work that's very relevant is by Emmanuel Todorov on things like linearly solvable Markov decision processes and the general duality between optimal control and estimation. Bert Kaplan studied this question extensively. One work on this is this one. Brian Ziebart has some very interesting work on maximum entropy as well as how it pertains to inverse reinforcement learning. Raulich et al. Has this paper that actually introduces a Q-learning algorithm based on soft optimality for shallow reinforcement learning. This is the paper on soft Q-learning that I showed previously. This paper by Natschman et al. Talks about n-step returns for soft Q-learning. And this paper by Schulman et al. Talks about the equivalence between policy gradients and Q-learning under the soft optimality framework. All right, and at this point, I'll let Chelsea continue with inverse reinforcement learning.
Okay, great. So a lot of this tutorial we talked about learning from reward functions, where our goal is to maximize the sum of expected rewards. But where does this reward function come from? So if you're in the realm of computer games, for example, you want your agent to be able to learn an Atari game, the reward function is quite clear. So the reward function can just be to maximize the score of the game. But in many real-world scenarios, it's quite unclear what the reward function is actually going to be. For example, in robotics, if you want a robot to be able to pour a cup of water from a pitcher, defining the real world doesn't just give you a reward function for how well you're doing at this task. And likewise for dialogue, if you want to be able to interact with a human, your reward function is probably some complex function of the emotions and how happy the person you're talking to is. And likewise for autonomous driving, the reward function is going to depend on very complex aspects of the world. So in many cases, if we're trying to apply reinforcement learning to these sorts of problems, we're going to use some sort of proxy. Like for autonomous driving, we might use a proxy to try to minimize collisions and maximize speed. But in many scenarios, it's actually easier to provide data, expert data, for how you want your agent to behave, rather than trying to engineer a reward function for a particular task. And so what we can actually do is try to infer the reward function from rollouts from the expert policy when trying to learn behavior from such expert data. And so this is the problem that's called inverse reinforcement learning. So the problem of trying to infer the reward function from a set of demonstrations, also known as inverse optimal control. And formally in this problem, we're given the state and action space, rollouts from an expert policy, which I'll denote with pi star, and sometimes a dynamics model. And then our goal is to recover the reward function, and then usually also use that reward function to acquire a policy for performing the task. So why is this a hard problem? Well, the first challenge with trying to solve this problem is that it's underdefined. So imagine this setup in your agent is the green circle here, and you see this expert rollout. The reward function that the expert was acting under could be a number of things. It could be trying to reach the blue triangle. It could be trying to move away from the red triangle. Or maybe it just wants to move right. And this means that the problem is underdefined. There's many possible reward functions that could be underlying the expert's behavior. Second, it's difficult to evaluate a reward function that you've estimated. So if you have an estimate of the reward function, how do you tell how good that estimate is? Well, one thing you can do is try to solve for the optimal policy under that reward function using forward reinforcement learning, and then put that policy to the expert policy, to the rollouts from the expert. But that requires running forward reinforcement learning just to be able to evaluate how good your estimate is. And lastly, the demonstrations that were provided may not be optimal. For example, if the demonstrations are coming from a human, they might make some mistakes as they're demonstrating. So a very popular framework for inverse reinforcement learning is based off of the graphical model that Sergey presented earlier. So this is called maximum entropy inverse reinforcement learning, introduced by Brian Ziebart in 2008. And what it does is it handles the ambiguity of inverse reinforcement learning by using a probabilistic model of behavior. And in particular, it actually uses the same probabilistic model that Sergey presented earlier, and I'll go into more detail in a second. So first, notation. I'm going to use tau to denote a trajectory, a sequence of states and actions. I'm going to use little r to denote the reward function parameterized by phi here. This could be, for example, a neural network, a linear function, a Gaussian process. And I'm going to use a capital R as shorthand to denote the reward, the sum of rewards over time of a trajectory. And then lastly, I'm going to use D to denote a set of expert demonstrations that are rollouts from an expert policy. So in the maximum entropy formulation, we're going to assume that, as Sergey discussed before, that the probability of a trajectory is going to be exponential in the reward. And so what this is saying is that the expert with the highest likelihood is going to demonstrate the optimal thing, and it will demonstrate suboptimal things with probability that's exponentially decreasing in the reward function. Then to find the reward function, given our demonstrations, we're just going to do max likelihood. So we're going to maximize the log probability of the probability of our trajectories under a reward function, and find the parameters of a reward function that maximize this probability. And for those of you that are familiar with EBMs, this is just an energy-based model for behavior. So where does this get tricky? So this seems like a pretty straightforward problem to solve. We know how to evaluate our reward function, but the tricky thing comes in right here. So this is the z, or the partition function. It's an integral over all possible trajectories of the exponential of the reward. And in simple settings, we can solve for z analytically, but as our dimensionality of our state and action space increases, and if we don't know the dynamics, this is very hard to compute. So next I'll go over just the algorithm of maximum entropy inverse RL. So first we initialize the parameters of our reward function and gather our demonstrations. Then solve for the optimal policy with respect to our current estimate of the reward. In step 2, we solve for the state visitation frequencies. This is the forward messages that Sergey was talking about earlier. And then we compute the gradient with respect to our reward function, which is given here, which uses those state visitation frequencies to estimate the gradient of inverse reinforcement learning to update our reward. And then lastly, we update the parameters of our reward with one gradient step using the gradient that we computed. And then we repeat. So notice that this algorithm requires solving the MDP, solving for the optimal policy, in the inner loop of solving for the reward function. Which, as you might imagine, is quite expensive and won't scale well to more complex problems. So how can we, one, handle unknown dynamics, which is the setting in most problems that we care about, and second, avoid solving the MDP in the inner loop of inverse reinforcement learning. So here's the problem setting again, and what we can do is, to estimate z, we can use samples. So we can collect samples from our policy, and then use that to estimate our partition function. So how well work? Well, how well will this work? Well, if you look at this quantity, to be able to accurately estimate this quantity, we'll need to sample from a distribution that is ideally close to the distribution that's proportional to the exponential of the reward function. And this requires the optimal reward function. And this requires that we know the optimal reward function, which is what we're trying to solve for in the first place. So if we just sample from some fixed distribution without knowing the optimal reward function, then we aren't going to be able to accurately estimate this quantity. So what we can do instead is adaptively sample to estimate the partition function. And what this involves is we're going to adaptively construct a probability distribution that gets closer and closer to the probability distribution that's proportional to the exponential of the reward function. And the way that we can do this is by constructing a policy. So how does this work? So this was work that was presented in these two papers and was presented in the form of guided cost learning or generative adversarial imitation learning. There is a couple differences between the algorithms, which I'll outline a bit later, but the overall structure of the algorithms are the same. The inputs to the algorithms are an initial policy and a set of human demonstrations. Then you can take your initial policy and generate samples from that policy. That's the first step. And then you're going to use those samples to estimate the partition function, as well as use the demonstrations to update your reward function using the samples and the demonstrations. Then once we have our estimate of the reward function, we're then going to update our policy with respect to that reward function to try and get a better trajectory distribution to estimate our reward function, to estimate the partition function in the IRL objective. And then once we have our updated policy, we're then going to generate more samples from that policy and then update our reward function again and iteratively alternate between updating the policy and generating samples from that policy and updating the reward function. And then at the end of this process, we'll end up with the reward function underlying the human demonstrations and a policy that optimizes that reward function. Okay, so how do we avoid solving the MDP in the inner loop of this optimization? Well, instead of fully solving for the optimal policy, we only partially optimize. So we're going to take one iteration of policy optimization with respect to our current reward function. Okay, so that's the algorithm at a glance. For those of you that are familiar with generative adversarial networks, this actually looks a lot like a generative adversarial network. So the goal of the policy is to generate samples that look a lot like the data, that look like the demonstration data. And the goal of the reward function is to assign high reward to the demonstrations and low reward to the samples generated from the policy. And interestingly, it turns out that for a certain form of the discriminator, maximum entropy inverse reinforcement learning using samples to estimate the partition function is mathematically equivalent to generative adversarial networks. Quickly, what are generative adversarial networks? Similar to inverse RL, GANs learn an objective for generative modeling. And you could do cool things like turn a horse into a zebra, generate faces of people, or translate from edges to cats. So what is the relationship between inverse RL and GANs? Well, in inverse RL, we're dealing with trajectories, whereas in GANs, we're dealing with samples or data points. In inverse RL, we are using a policy to generate samples. This corresponds to the generator in a GAN. And the reward function in inverse RL corresponds to the discriminator in GANs. And I'll also use P to denote the data distribution. So first, let's look at the optimization for the reward function or the discriminator. In the guided cost learning algorithm, what this looks like is the discriminator is actually going to take a special form. The optimal discriminator is for a discriminator that's trying to output the probability that a sample came from the data. The optimal discriminator will be the ratio between P over P plus Q. And we're using an energy-based model that uses a Boltzmann distribution to represent P. So we're just going to replace P with the exponential of the reward function. In generative adversarial imitation learning, instead of using the special form of discriminator, they just have D be some classifier, just like in the typical GAN setting. And then the objective for both of these methods, as well as for GANs, is this objective right here. Okay, and then next let's look at the policy optimization. So in a GAN, the generator objective is to be able to trick the discriminator. This is the objective. And this is equivalent to maximizing the negative entropy plus a constant minus the reward function. And this is just entropy regularized reinforcement learning. So this is the objective that we're using to train our policy. And there's one more difference between the typical GAN setting and the inverse reinforcement learning setting, which is that because we don't know the dynamics, we can't just backpropagate through our discriminator into the policy. We actually need to train our generator or our policy with reinforcement learning. That said, there is also a paper at ICML this year which used a learned dynamics model to backprop through the discriminator into the policy. And I'll talk a bit more about backpropping through models in the next section. Okay, so what can you do with these methods? So this is a video of me collecting demonstrations on the PR2 robot. We can then infer the reward function using guided cost learning underlying these demonstrations, and then optimize that, and this is the resulting policy that it learned. And then here's some examples of a paper that followed up on the generative adversarial imitation learning paper, and they showed that using motion capture data collected from humans, you could learn how to walk and also learn how to fall and get back up again. Okay, so just to recap, the goal of inverse RL is to infer the reward function underlying expert demonstrations. The main challenge is evaluating the partition function. And initial approaches evaluate the partition function by solving the MDP in the inner loop of inverse reinforcement learning, or assuming known dynamics. And with unknown dynamics, we can estimate Z using samples. And then I also talked about the connection to generative adversarial networks, showing that sampling-based maxent inverse reinforcement learning is a GAN with a special form of discriminator, and using reinforcement learning to optimize the generator. Next, some suggested readings on inverse reinforcement learning. So first, the classic papers at Beal and Ng is a good introduction to inverse reinforcement learning. And here is the paper that introduces maximum entropy inverse reinforcement learning. More modern papers, these papers are some of the first papers to use deep neural network function approximators to represent the reward function, including this paper by Marcus Wolfmeyer, the guided cost learning paper, as well as Ho and Erman. And so for further reading, you can also see some of these papers, which have considered more challenging inverse reinforcement learning settings, such as handling multimodal demonstrations and handling domain shift between the demonstrations and the agent that's trying to learn the policy. Okay, so that's the end of inverse reinforcement learning. Next, I'm going to be talking about model-based reinforcement learning. So everything that we've talked about so far is what's considered as model-free reinforcement learning, in that it doesn't involve trying to learn the dynamics model. And so the key idea behind model-based reinforcement learning is to learn a model of the environment, trying to learn the dynamics model. And so why do we want to do this? Well, typically these sorts of methods are much more efficient in terms of the amount of data that you have to collect in the environment. So let's bring back this diagram where we have this cycle of generating samples, fitting a model to estimate the return, and improving the policy. In the model-based setting, what we're going to do to fit a model is directly estimating the dynamics using some function approximator f. We can do this with supervised learning just by trying to minimize the error between what we predicted as the next state and the actual next state. And then once we have our estimate of the model, we're going to optimize our policy using that model. And next, we'll talk about one way in which we can do that. Okay, so one way you can do that is by backpropagating our gradients through the model into the policy to update the parameters of our policy. So consider this flowchart of what reinforcement learning looks like. So the input, the policy outputs an action. The model takes in the state in action and outputs the next state, which can be then fed into the model and the policy. And we also have a reward function that takes in a state in action and outputs the reward. What we can do is if we have a parameterized model of our function, as well as a parameterized model of our reward function, we can just backpropagate our objective of the maximizing the sum of rewards into our policy, basically through our model for the reward function and through our model of the dynamics into the parameters of our policy. What this looks like as an algorithm is first we run our base policy to collect some data, then learn a model using that data to minimize the modeling error. Third, backpropagate through the model into the policy to optimize our policy. And then run our policy, appending the visited tuples to our data set. And then go back to step 2 and iterate, refitting our model using the new data that we collected. Okay, so this is a reasonable approach, and sometimes it works well, but sometimes it doesn't work well. And the reason why it doesn't work well is that oftentimes policy optimization can exploit imprecisions in the model. So if the model has some imprecisions and it can't is inaccurately predicting that if the car turns left, it will actually go straight, then the policy will start going there and try to find areas of the state space that have low reward. One thing that we can do to mitigate this that I presented in the algorithm previously is that we can refit the model using data collected from our policy. But generally, learning a good global model of the entire environment is hard. So what's one more way that we can mitigate the fact that learning a good global model is hard? Well, one thing we can do is, as we take actions, we can replan in real time to try to correct for mistakes that we may have made. This is what's called model predictive control. So the way that this works is we first run our base policy to collect a data set, learn a model to minimize the modeling error, backpropagate through our model to choose actions, a sequence of actions that we want to take in the future, then execute the first planned action, observe the resulting state, and of course append our what we saw to the data set. And then at the next time step, again, backpropagate to choose the next sequence of actions that we want to take. And including this loop here allows the method to fix mistakes that it may have made. So if it made a mistake when it was planning, then it will observe a new state. Maybe that wasn't the state that it expected, and then it can replan using its model to try to correct for the mistake that it made to get back on track. And then once you collect data by planning with the model, you can then repeat the whole process of refitting your model with the data that you observed and resampling. So what this algorithm does is it just changes how we're generating samples and it turns the policy into a policy that's implicit, that is determined by planning through the model. And as a result, this helps with model errors. So one of the benefits of this is that we can replan to correct for model errors. One of the downsides, though, is it's very compute intensive because you actually have to do this planning and replanning in real time as you're executing actions. Okay, and then a third approach that we can do to try to mitigate the difficulty of learning good global models is by instead learning local models. So what this entails is first running our policy again to collect data. And instead of trying to learn like a global model for the entire world, just refining ourselves to a small space and trying to learn a local model around the trajectories that we collected in that data set. And we can do this, for example, with if you have a time-varying linear model that's local to the trajectories, you can do this with linear regression. If you want to improve your efficiency, you can also do this with a prior. For details, you can see the paper that's linked up there. Once we have our local model, we can then update a policy that uses the local model, but constrain the policy to stay close to the data, stay close to the distribution in which the data was collected. So you want to improve your policy a little bit where you know the model is good, but not try to stray outside of the realm, outside of the area in which the model is good. And then once you have your updated policy, you can then run this policy, put tuples in your data set, and repeat. So relearn a local model on your new data set around the trajectories that you observed and update your local policy. So this can be pretty effective for learning a wide variety of skills, but it can only learn skills in one local region. For example, for one initial condition and maybe one target position of where you want to end up. So one way that you can try to learn a wider variety of skills is to supervise a single global policy using multiple of these local policies. So I'll give an example next. So say your goal is, well, in reinforcement learning, our goal is to maximize the reward under the policy. And ultimately, we want to be able to do this with high-dimensional observations like images. But if we do this directly with images, we're going to be quite inefficient to try and learn that mapping from scratch. So instead of trying to learn it from scratch with images, we can instead try to learn it from the raw states if we know the raw states at training time. So if we know the true state of the system, for example, the target pose, where the shape sorting cube is in this example, we can then more efficiently solve the problem. So what guided policy search looks like is we're going to decompose the problem for different target positions, so different positions of the shape sorting cube, fit a local model, and solve for the local policy for each of the target positions. And then once we have a local policy for each of those target positions, we can use supervision from the local policies to train a single global neural network policy that can solve the problem for all positions of the shape sorting cube. And what you can do is instead of training that single global policy on states of the system, you can actually don't give it the target position, but instead give it the image and have it learn to map from images or raw observations, high-dimensional observations, to the target actions that it wants to achieve. This isn't specific to just putting a block into a shape-sorting cube. You can also do this for other problems by decomposing them into these sorts of subproblems, solving for local policies for each of those subproblems, and then supervising a single global policy. So this is what learning looks like. So as you can here, you can see the robot starting from scratch. It's moving its arm around randomly initially. And then it's learning a local policy for each position of the shape-sorting cube, and using that supervision to train a single global policy for inserting the block into the shape-sorting cube. And so eventually, you'll see after around 25 minutes of robot time, the robot can learn a policy that maps from raw images to the torques of the robot arm for achieving a single task. It's 25 minutes per task. And it can learn how to do things like placing a claw of a toy hammer underneath a nail, inserting a bottle cap into a bottle, etc. And so one of the benefits of an approach like this is you can efficiently learn complex vision-based skills. One downside is that it does require the full state information during training so that you can learn very efficiently. Okay, so from there, what if we only have access to high-dimensional observations during training? What if we can never observe where the shape-sorting cube is, or never observe the true low-dimensional state of your problem? So this is what your MDP, this is what your model would look like in this setting. And perhaps as an example, to intuitively look at this problem is maybe your robot wants to take a spatula and lift an object into a bowl. But it doesn't get to observe where the object is. It can observe maybe where its hand is, but it can't observe where the bowl is, where the object is. And also, typically, in this setting, if you don't know where this object is, where the white object is, for example, you don't have a reward signal in this setting as well. So one way that you can try to get a reward function is by providing an image of the goal. There are other ways to do this as well, which I won't cover in this tutorial. So two approaches for solving this setting. One is to try and learn a latent space and learn a model in that latent space, and then perform model-based RL in that low-dimensional latent space. Another method is to learn a model of your raw observations and just perform model-based reinforcement learning in that high-dimensional space. And then another area that I won't cover today is using inverse models. Okay, so the key idea behind learning from a latent space is to learn some embedding of your observations G, and then perform model-based reinforcement learning in that latent space. So what this is going to look like is if you have this diagram here, then you're going to be learning a mapping G that goes back from your observations to your true states. Without access to the true states, you're just going to try and infer that from the data, and then perform reinforcement learning in your state space. So there are two papers that I'm going to cover, that I'm going to show today that use this approach. What this looks like as an algorithm is first we're going to run our base policy, for example, an exploratory policy or a random policy to collect a data set, learn a latent embedding of the observations, and a dynamics model in that latent space. Then third, use the model to optimize a policy in that latent space again. And then you can run your policy using both the embedding function and your learned policy on the embeddings, and append the visiting tuples, and then repeat. So first, what is your reward function when you optimize your policy in the latent space? The reward function that both of these methods use is just the reward function of the actions and the negative distance between the embedding of the current observation and the embedding of the goal observation. So you assume you have some sort of goal image like I mentioned before. And then second, how do we optimize for a latent embedding? So this is a much trickier problem. This is one of the problems underlying unsupervised learning. In the paper by Water et al., they learned an embedding and a model jointly to try and learn a latent space that is predictable, as well as using an auto-encoding objective to try and be able to reconstruct the current frame. And then in this paper, we tried to learn a latent space that's structured. So what we did is we had an autoencoder, and the bottleneck of the autoencoder enforced that the features represented feature points, 2D coordinates in the image. And this won't work for all problems, but it provides a nice structure for the policy to be able to learn things that rely on the spatial positions of objects. Okay, so with these methods, you can, for example, learn to reach some goal state. So that the goal image was shown previously, and now you can see the policy learning to achieve that goal image. And this is all from images, so it doesn't observe the positions, the joint angles of the arm, for example. And it learned how to do this with only around 25 minutes of robot time. And likewise, you can also, in the other paper that I showed, it learned how to do skills like pushing a Lego block, transferring an object, and using a spatula to pick up an object to put it into a bowl, all from raw images. And in this particular paper, the skills took around 11 minutes of robot time to learn, which is significantly more efficient than what you can get with model-free methods. Okay, so some of the pros, we can learn complex skills very efficiently, and the structured representation can enable effective learning. Yeah.
Is that 11 minutes including data to create the embedding, or 11 minutes of data with the?
Yeah, so it was 11 minutes, including the data that was used to train the model, and the data that was actually, once you have the model, to train the policy. And then one of the disadvantages of this approach is that learning that latent space, typically you use a reconstruction objective or something similar, and those objectives might not recover the right representation for solving the task. And if they don't recover, if they discard some of the information that's crucial to solving the task, then you won't be able to learn a policy effectively. Okay, also a low-dimensional embedding like this can also be useful for model-free approaches. So you can also learn a latent space and perform model-free in a latent space. So a paper that in 2012 used fitted queue iteration in a latent space to be able to learn a policy on a toy slot car. And a more recent paper performed trust region policy optimization on a real robot in a latent space to be able to very quickly learn a policy, I think in this case, throwing a ball onto an object. You can also use an embedding for a reward function. So this paper used ImageNet features to represent the reward function, combined with model-free reinforcement learning to be able to learn how to open a door from a raw video on a robot. And then lastly, if you have a reward function, you can also use that to improve learning a latent space. So if you have a reward function at training time, if you predict that reward function and make your latent space, making the ability to predict the reward function from your latent space, then your latent space should capture information about the task and improve your latent space. Okay, I don't think I have time to cover this in the tutorial, but this entails essentially just learning a model directly in your observation space, which can work even on real robotic systems and be able to learn from purely unsupervised data in around 2 days and learn for a wide variety of skills. Okay, so to review, in model-based reinforcement learning, you fit a model of your dynamics function, which you can do with supervised learning, and then optimize your policy, which you can do, for example, by backpropagating through your model. One of the key challenges in model-based reinforcement learning is correcting for model errors, and you can do this by refitting model with new data, replanning with model predictive control, and by using local models. You can also perform model-based reinforcement learning from raw observations by learning a latent space, typically with unsupervised learning, or by modeling and planning directly in your observational space. Here are some suggested readings on model-based reinforcement learning. So here's a good introduction to model predictive control with a known model by Yuval Tassa et al. Here's the guided policy search paper. Here is a paper that backpropagates through a model to assist a model-free learner. Here's the embedded control paper that learned a latent space and used model-based reinforcement learning in the learned latent space to reach an image of the goal. And lastly, here's a paper that plans using a learned action condition video prediction model, so planning in the raw observational space. Here's some further reading on model-based reinforcement learning. One thing that I didn't cover today was there's been a number of methods that have tried to combine model-based reinforcement learning and model-free reinforcement learning to try and get the benefits of both methods. And so some approaches that people have tried to do in this setting is to use rollouts from the model as experience, try to use the model as a baseline to reduce the variance of your policy gradient, use the model for better exploration, develop a model-free policy with the capabilities of planning, and lastly, using a model-based look-ahead when trying to learn your policy. Okay, and before I wrap up with the last part of this tutorial, I'd like to quickly compare model-based and model-free reinforcement learning methods. So the benefits of a model-based approach is that you can easily collect data in a scalable way. It's often completely self-supervised without the need for a reward function. And there's a possibility of transferring across tasks. So if you learn a model of the environment, then you can actually not just achieve a single skill as you can in model. So in model-free reinforcement learning, you're learning a policy. And that policy will do one thing, or maybe a couple things. But in model-based reinforcement learning, you're learning a model of the environment. And if you can plan through that model, you can actually plan to achieve multiple goals and achieve multiple skills. And typically with model-based methods, you can require a smaller quantity of supervised data, so a smaller quantity of data that requires reward functions. One of the downsides is that models don't directly optimize for task performance. They optimize for the ability to predict the next state. And sometimes it's harder to learn a model than to learn a policy because the model has to pay attention to things that aren't relevant for the task. And you often need some sort of assumptions to learn complex skills, such as continuity and resets. In model-free reinforcement learning, they make very little assumptions beyond the need for a reward function during training and are very effective for learning complex policies. The disadvantages is that typically they require a lot more experience, so they're much slower, and they're not transferable across tasks, as I mentioned before. Okay, so lastly, I would like to talk about some of the frontiers and open challenges in deep reinforcement learning and decision making. So what's missing for these algorithms to be practical for real world problems? And also, what is needed for us to be able to reach agents that can achieve human level decision making? So I think there's, these might not be the only questions, but I think I'm going to bring up 3 questions that I think get at this question of what's missing. First, how can our agents learn effectively using much less experience? So typically reinforcement learning algorithms require quite a large amount of experience, and we want to be able to, humans can learn from much less. How can we also ensure that our agents explore safely, which is crucial for deploying these systems in real world settings? And then lastly, where do the rewards come from? How do we ensure that these methods are actually doing what we want them to do? So in the next slides, I'm going to talk about initial approaches towards solving these problems. These problems are by no means solved. I'm going to show a number of papers, and these papers are just initial approaches. Okay, so first, reducing sample complexity. So a scalar reward function is a very sparse signal, while at the same time, humans can actually learn without any external reward function. So a human can actually solve Atari games without actually looking at the reward function. So how can we improve efficiency? Well, a number of papers have looked at trying to improve exploration and self-supervision by essentially adding objectives to increase things like the intrinsic curiosity of the agent. And here are some recent papers on that. People have also looked at options and hierarchy to try and learn higher level actions and higher levels of abstraction for solving these sorts of problems. There's a couple papers on leveraging stochastic policies for better exploration. And then there's also been a couple of recent works on utilizing auxiliary objectives beyond the reward function for more effective and faster learning. And then another way that we can reduce sample complexity is inspired by this example. So humans don't learn individual complex tasks from scratch. So here's a baby, and the baby can't learn how to play Atari games from scratch without a lot of playing and rolling around on the floor. And so maybe our agents shouldn't be able to learn a single complex task either. And ultimately, we don't want our agents just to be able to perform a single task. We want our agents to be able to perform many different tasks in many different environments. So one thing we could do is we could try to have our agents be able to learn how to learn new tasks quickly. And this is something that humans are able to do. And maybe there are other ways that we can share information across tasks so that when our agent is learning multiple tasks, when it tries to learn a new task, it can learn much more quickly. If we're going to have our agent learn a lot of different tasks, well, where should those tasks come from? So there's also been some recent works on trying to automatically generate tasks and automatically generate curriculums for learning. Okay, and so the second point is, how do we ensure safety? Again, I don't know the answer to this question, but there's been some recent works on trying to incorporate uncertainty for making our agents safely explore. You can also learn from off-policy data. So if you can learn just from other data, for example, that humans collected, then our agents might be able to not actually have to run an unsafe policy in the real world. We can also involve human interventions when it looks like the agent is going to make an unsafe decision, as well as introduce probabilistic constraints on what our policy can do and cannot do. And then lastly, another popular approach has been to train entirely in a simulated world and learn and then try and transfer what was learned in simulation to be able to effectively act in the real world. And these are all approaches that might bring us closer to safely exploring the environment. Okay, and then lastly, where are we going to get reward functions? How can we tell our agent what we want it to do? So there's been a couple works on proposing new ways to learn reward functions from humans. One possibility is to learn from human preferences, from pairwise preferences of is this state better than this state? Or also trying to cooperatively learn the reward function, having the agent trying to infer the reward function cooperatively with the human. And there are other forms of goals that we can provide to our robots. So I talked about inverse reinforcement learning to try and get the goal from a set of demonstrations. We could also try to infer the reward function from a video of a human or a goal image. And we could also try to specify where objects will move in an image. And these are just a couple possibilities. I think there's a lot of room for exploration and interesting directions in this problem. And lastly, there's been a couple of recent works on trying to give language instructions to the robot. Okay, so that was the end of the main content of the tutorial. I'd like to end on a closing thought. So most deep learning systems today that are deployed in real problems are using supervised learning. But supervised learning is again, showing this example, supervised learning is quite different from how humans learn. So in supervised learning, you have to manually collect a data set of input and output pairs and train the system to try and produce a given output for a given input. This requires a lot of manual effort and a lot of supervision. Whereas in a setting like reinforcement learning and providing rewards, there's a lot less supervision that's involved. And maybe if we gave our agents less supervision and forced it to learn and figure out more about the world on its own, maybe it would be able to get closer to human level abilities. Okay, again, the slides are online. Here's some more resources, and thank you for listening.